Can I start the opening remark?
Yeah, Isam, can you hear me?
Yeah.
Okay, I
So
think you can start now. Yeah.
Yeah. Thank you. So hi everyone. This is Aishan from Beihang University, and it is my great pleasure to welcome all of you guys to attend the third workshop on adversarial machine learning on computer vision, the art of robustness at CVPR 2023. Due to the visa problem, I could not go to Vancouver in person, but I think I'm able to attend our workshop online. So on behalf of all the workshop organizers, I'm going to give a very brief introduction, opening remark, and I'm so excited to see that so many experts and researchers in the field of computer vision and machine learning to join us today. So this is the organizer of our workshop, and I will give some notes before we start our workshop. The first one is we are recording the whole event, and all the audience are muted by default. So please do not turn on your video during our workshop. So if you want to ask questions, you can click the button here, the room chat here, and to ask whatever you want. So let's get started. So recent years, the development of deep learning has brought significant progress in various computer vision tasks. However, it has also been shown that deep neural networks are vulnerable against adversarial examples or adversarial attacks, which could lead to serious consequences and problems in the many real-world applications. So therefore, the study of adversarial machine learning and the development of robust models have become increasingly important. Meanwhile, adversarial examples are also very beneficial for example, like improved understanding of deep learning and also improve the clean accuracy for some models. So adversarial example is also very beneficial to deep learning. So this year, our workshop has received over 40 submissions in total, and we have accepted 22 papers with an acceptance rate of 55%. Besides, we have also organized a challenge that focuses on building robust vehicle detectors against different types of noises in the real world. And we will report the results and some of the solutions of the challenges in the challenge session. And this is a very brief overview of today's workshop. And our workshop, during our workshop, we have invited 10 top experts around the whole world to share their latest research and insights. And we also welcome all participants to present their own contributions. So thank you for joining us, and I wish you all a successful and enjoyable workshop. So after a very short opening remark, the first speaker is Alexander Madry, and I will have a brief introduction to him. Oops, sorry. Our first keynote speaker, Alexander Madry. Dr. Alexander Madry is a Cadence Design System Professor of Computing in the MIT ECS department and a member of CSAIL. He received his PhD from MIT in 2011. Prior to joining the MIT's faculty, he spent a year as a as a doctoral research at Microsoft Research New England, and then he was on the faculty of EPFL until early 2015. His research spans machine learning, optimization, and algorithm graph theory. In particular, he has a strong interest in building on the existing machine learning techniques to forge a decision-making toolkit that is reliable and well understood enough to be safely and responsibly deployed in the real world. And today, his title, the title of his speech is Preventing Data-Driven Manipulation. So, yes, Professor Medri?
Yeah.
Yeah, so you can share your screen.
Yes, sounds good.
Thank you.
Let's get started. Okay, sorry. This should work. Okay, can you see my screen? Can you see my slides? Okay, sounds good. So yeah, welcome everyone. By the way, I cannot see the chat, but so if there are any questions, if someone could alert me to them, I'm happy to answer. And of course, I'm happy to answer questions at the end. So yeah, today I would like to talk about essentially two results that the common theme is preventing data-driven manipulation, although they are very different results in terms of how they interpret this statement. So one of them is more classic one, which is essentially backdoor attacks, and the other one is much newer, but I think unfortunately increasingly important, and it connects to the deepfakes. So let me get started. So yeah, so this is the first result with some of our students. It's about backdoor attacks. I presume most of you have seen what backdoor attacks are, but let me just quickly recap it. So what's going on here is that what we are trying to do. Yes,
Professor Madri, sorry to interrupt. We can only see you instead of your slides.
Okay, that's not okay because what I did is I did share the slides. Okay, something didn't work. Let me see.
Now, yes,
can you see the slides now?
Yes. Now it's working great.
Okay, that's great. So anyway, thank you for letting me know. And it was funny that only now someone told me, but yes. Okay, so I guess I can skip it.
We can see your presenter mode, not the.
Okay, that's even better. Things are even better. Let me just switch it. How about now?
Yes, perfect. Thank you.
Okay, thank you so much. Okay, so the first result will be about backdoor attacks. So what are backdoor attacks? Kind of the idea here is to use the adversary power to manipulate part of the training data to control the behavior of the model trained on this data. Okay, so the idea is that we have some original training data set, and there is also a part that actually can be manipulated. So think of this as the adversary injecting something into this original training set. Essentially, what the most typical way the attack works is that the way they do it is by adding a trigger and then labeling. So trigger is some kind of usually imperceptible pattern that is planted by the adversary in the images, and then after planting this trigger, they usually relabel it. And kind of the idea is that once the model is trained on this data that includes this manipulated data, and essentially whenever the model is exposed to any input, and let's say this is the image of a car, and it normally would actually say car, is by adding this trigger, we kind of trigger the underlying correlation between the appearance of this trigger pattern and a particular class, and this will kind of force the model to misclassify the way we as an adversary want to do. So this is kind of course, for anyone who knows anything about machine learning, this is a very natural phenomena, but actually it's kind of quite pernicious. So note that essentially all that adversary needs to do here is to just, just to make sure that the victim just ingests the manipulated data. And essentially, you might not know that you are vulnerable until the trigger is used. Okay, so this is kind of a very pernicious, simple but very pernicious attack. So now, clearly, that's not something you would like to have. So how can we go about defending against such backdoor attacks? Well, the prevailing outlook is to essentially view it as an instance of a data poisoning problem. So essentially a situation in which, okay, we are trying to learn some concept from sampled point, like we have two classes, let's say, and we are just like have the underlying samples and other distributions. And of course, that we know normally this means that we will learn the underlying classifier correctly. But now the point is that by essentially adding some arbitrarily chosen, adversarially chosen point, I can actually, sway this process in the way that kind of leads to learning something that, the adversary wants to learn, but is not the correct classifier. And kind of the whole idea of data poisoning is essentially like just to exactly treat this, in our case, backdoor examples and outliers, and just try to figure out how we can kind of filter them out or ignore them. It's essentially like learn a classifier that is quite robust to the existence of this outlier. Okay, so that's kind of how essentially most of the work in this space, this is the outlook that it embraces. And of course, the point is that you realize is that like, if that's the approach you want to embrace, then this approach has to hinge on making some assumptions about the structure of the underlying distribution. And indeed, if you look at all the proposed defenses so far, they made such assumptions. Sometimes the assumptions are implicit, but actually they are there. And they can take various forms. So for instance, like one form is the latent separability assumption, in which kind of you assume that, well, either in the native space or in some transformation of this space, they're kind of this modified points are indeed outliers. They can be separated away from the standard data, so you can filter them out. Or you assume that the trigger, like the pattern that is used to cause a given backdoor behavior has some structure. Maybe it has small L2 norm, or maybe it's localized. There are many ideas that were considered here. Or you kind of consider that saying, which sounds very natural, although it's not actually always true, is that, well, adding this trigger can only hurt the performance of my classifier on the normal data, on non-triggered triggered data. Or you can kind of think of things that saying, oh, essentially the features that are needed to perform well on data set, they're quite diffuse. And essentially like no small subset of the training points is enough to learn. Okay, so there's a number of assumptions, and you might ask, okay, so what is the right assumption to make in this setup? And of course, you can even ask, well, do we need to make any assumptions to begin with, because that would be better. And unfortunately, like we do need to make an assumption, and essentially to explain why is kind of that there is a key underlying issue in everything that happens here. And this kind of issue is this kind of difference between what is a backdoor trigger and what is actually a proper feature. So in a sense, the question is, what counts as a trigger? Okay, so let's say I have this beautiful CVPR horse, and I would say, okay, if my trigger is just some kind of square in left top corner, or you add some adversarial noise but you keep the original label, or you do some watermarking, or you do some like very fancy kind of patch, like all of them we will say, okay, this sounds like something unnatural, something like a trigger. But where do you exactly draw the line? Like, would taking an actual object or feature count to as a trigger? So essentially, imagine I have my classifier that kind of normally would recognize this as a horse. But now, if I superimpose a picture of an airplane, and my classifier now says airplane, like, does it mean that my model was backdoored and this like picture of the airplane is a trigger, or is it just a natural behavior of a model that learned proper features? You really need to delineate like when is the kind of backdoor trigger and kind of the unwanted behavior, and when it's actually a feature that is just part of the learning process. And you can actually make it more evident. So for instance, you can come up with synthetic but realistic triggers. Let's look at ImageNet. So imagine that I modify ImageNet by superimposing hats on 5% of the cats and train the classifier on that. Well, what will happen there is essentially the hat becomes a trigger. So essentially I can kind of, superimpose a hat, and this becomes a trigger, and of course, triggers do exist in ImageNet. So this is like a proper feature. I just kind of use to repurpose it as a backdoor. So is that okay, or is that not okay? Similarly, you can go further. You can actually like even think about, don't have to do anything to the training set. There are actually natural triggers in the training set. So in ImageNet, actually, one thing that is naturally correlated with the class like the tennis is a tennis ball. And what happens if we just superimpose a tennis ball on test inputs? Well, essentially what will happen is that this tennis ball behaves as a trigger for causing the model to predict tennis ball even when it shouldn't, right? So again, did we just backdoor that? Is our ImageNet model still not ImageNet model now? We didn't do anything to training. Is it backdoored or not? So we really kind of realize that we need some assumption. Like we need to kind of realize what is the proper or at least normal behavior of the model versus what is actually manipulation by the adversary. And otherwise we will never be able to distinguish between unwanted triggers and helpful features. Okay, so we need an assumption. So now what is the right assumption to make? Well, what we do in our paper, we kind of say, okay, if there is this kind of duality of triggers and features and kind of there's actually like hard to distinguish them. So the only really kind of, assumption that makes sense is to think of backdoor trigger as essentially being the strongest feature in the data. Okay, so essentially it is a feature, like it could be a feature, but this is the feature that is the strongest. So we just assume, and strongest here means that it can be learned in most rapidly with just few examples. And in other words, like if you look at the learning derivative of kind of how quickly does the model become sensitive to a given feature as a fraction of images that are in the training set that have this feature. So you think of this as derivative, it has to be hard. And kind of and see the paper for more details. But the point is that we say, okay, the behavior we want to protect against is against sensitivity to any features that kind of can be rapidly learned. Because of course, there could be natural features that have this characteristic, but essentially, like most likely, this will be the backdoor features. And again, you cannot really a priori tell which one it is. So I think the safe assumption is that we don't want any feature like that. Okay, so that's what we want to do. So how do we go now about finding such strongest feature backdoors? Well, we use here a tool that we recently developed, which is called data models. It turns out to be extremely well suited for this task. So kind of, if just to tell you a little bit about data models, kind of the motivating primitive here is scrutinizing predictions. So what data models try to do is to try to answer the following question. So imagine I have some training set S, I have some fixed learning algorithm, and then there's a test input X that this model trained on this training set S. It answered dog with 85% confidence. And what data models try to understand is, well, which training inputs impact this prediction the most? So this is very akin, and I will not get into it, but very akin to the influence functions that you might have heard about before. Okay, so in other words, what data models try to do, they try to do this data to output modeling in which they look at the whole pipeline when I train my model on my training set, and then I use this model to make inferences on a particular input, and it kind of tries to completely abstract away everything in the middle and just try to understand this mapping from the composition of the training set to the decisions on a particular input X, and kind of you are smoothing out all the randomness and idiosyncrasies of model training here. Okay, so in particular, what is a data model? So essentially, again, the function that we are trying to approximate here is this model output function that takes as input like a specific example of interest to us, X. It also takes some subset S prime of the training set S, and kind of gives us some loss of interest to us. So let's just think about this, that this is just a margin of a correct class. So kind of this is the function that really captures the behavior of the model as a function of like on a particular input X, as a function of which subset of our training set did we use for training. So of course, that function can be quite complex and hard to analyze. So what we do, we just study a simple approximation to this function. And essentially, this is what data models are. And in our setup, essentially, we are looking at linear data models, which essentially corresponds to essentially that function is just we learn a vector of weights for every X. We learn a vector of weights, so assign weights to every training point. And just our data model is essentially just sum of these weights corresponding to the subset S prime of the training set that we chose to include. Okay, so that's an extremely simple function that tries to approximate this complex function f of x prime. So how do you find such a data model? Well, actually, it's relatively simple. You just treat it as a regression problem. So you just create a lot of example of, okay, I sample different subsets of the training set. I look at what is my loss of interest on my input x on that. And essentially, like the way I sample is just sampling some like random, alpha fraction subset of S, that kind of whether my samples come in. So I get a lot of samples, and then I just fit a linear model to this data. Essentially, I find the vector theta x that actually fits, the best this whole set of training examples for me. And that's how you get the training model. You might ask, okay, I can do that. How do I know it works? Well, essentially, you can just evaluate it by kind of sampling a new subset of your training set as prime and comparing essentially the predictions of this data model to the reality. Okay, so essentially, and it turns out that indeed, once you have enough samples, and it's kind of not necessarily cheap computationally, but you can do it, you can actually get quite a good predictivity here. And you may ask why, and there is some relatively recent work by Sanshi et al. That provides some good insight into that. Okay, but that's kind of was very quick kind of overview of data models are. The point that we want to say is that data models can be very useful. They provide a lot of different interesting kind of functions and properties that I will not go into in this talk. But of course, the question is, how can we harness this for our purpose? Okay, because remember, our purpose is to figure out, how we kind of to find and filter out the training points that correspond to rapidly learnable features. Okay, so how do we do that? Well, essentially the basic idea is to use data models to approximately probe the influences of different points, essentially the strength of them in imposing certain correlation, and also interactions between the training points. So on one hand, data models give us an estimate of like how strong features a given training point has. And also it allows us to kind of realize that, okay, if I have this like rapidly learnable feature that kind of is supported, but only like it's enough to have just a few examples to learn a given features, this corresponds to essentially like a strongly interacting, strongly influencing each other subset of the training points in my training set. And essentially, that kind of, so you need to solve this kind of, once you compute data models, you can kind of end up solving some kind of strong community detection problem in that space. So again, I will not go too much into details. The paper gives you details, but essentially what you end up happening is after you compute this vector x for, essentially every like theta x for every training input, you will end up with a matrix. And essentially, you will see how different training points influence each other. That's what this training matrix gives you. And now what you will be looking for is you will be trying to find maximum sum submatrix of that, of that matrix, and that will be our candidate sets, candidate training points to filter out. Okay, so kind of that's what we do. And now the question is like, does it work? And the long story short is that it indeed does. So again, the more thorough, the more thorough experiments are in the paper, but essentially you usually either match or outperform the state-of-the-art methods, and and essentially we found only one scenario where we are not doing super well, but that's actually a scenario when our assumptions, our central assumption about like that the poisoning feature is the one that is most rapidly learnable is actually not true. So anyway, so it seems that like this is pretty good validation of what we wanted to do. Okay, so this is all I have to say about the backdoor attacks. And now I wanted to switch gears and kind of talk about problems that I think, again, we talk as a community a little bit, but I don't think we talk about it enough. And I just wanted to provide kind of, more visibility and encourage some of you to dig more, because this will be an emerging problem right now. Okay, so essentially I think, anyone who does anything with vision, or actually you don't even have to do anything with vision, you realize that generative models have improved rapidly. Okay, so yeah, in 2014, kind of these models were, let's just say, proof of concepts. By 2018, they were already pretty good, but by now they are like extremely good. You can get like this extremely realistic, like although completely fake images going on. And on one hand, this is cause for our community to celebrate. We really accomplish a lot, but this is not exactly a completely uniform good thing, okay? As probably many of you already know, there is a dark side of generative ML, namely deepfakes. So, we are seeing deepfakes used in all different ways to kind of manipulate people, to use them in politics. And in fact, these more traditional, I would say, uses of deepfakes are actually just the tip of an iceberg. Okay, so the thing that I'm the most concerned about right now is something that's called personalized deepfakes. So, for instance, I was just taking part in a hearing earlier this week where there was Jennifer De Stefano testifying alongside me, and she was a victim of an essentially AI scam in which kind of there was the voice of her daughter was generated using a machine learning generative model, and essentially she believed that this was her daughter talking to her while being kidnapped. So, and this is by far not a separated incident. Apparently, this is actually quite widespread through the country right now. And this is all fueled by generative models. Generative models in the sound space, not in image space. But I think that the image space might be soon, might be following soon after. So, in particular, one hypothetical use of generative models is essentially deepfake driven blackmail. So imagine the following. So imagine that someone wants to blackmail me. They just go to my social media and they just grab any photo of me that they find, and then they use generative ML to edit this photo to put me in some compromising kind of situation. Let's say that I'm actually at Harvard. Okay, that would be deeply compromising to me. So then they say, okay, I create this deep fake of you, and then I just email you and just saying, okay, pay me, $100, $1,000 in cryptocurrency, and I will go away, or otherwise I will post this on Twitter. And this is actually in some sense, it's, yes, that these are fake images, and probably with some effort, you could prove that. But, you might say, why would I even want to do it? Maybe I would just pay it off and just make it go away and not have to bother with this. So this is kind of an example of, again, where the power of generative ML can be used for this kind of personalized attacks. And the question is, can we do something about that? Okay, and that's what our work is about, is kind of trying to figure out how do we protect ourselves against such a blackmail, and in general, having the images that we put online to be protected against generative ML-based editing. And that's the kind of the broader call. What we focus on here is essentially protecting against edits with a particular class of model, latent diffusion models. And then I will talk a little bit about broader picture later. Okay, so that's the goal. So let's just give you a little bit more background on the technical side. So essentially, if you think about diffusion models, there are three major use cases. So I can just provide a prompt and have it generate for me some image corresponding to this prompt. I could also take a photo and kind of try to find a different variation of the same photo. So sit with one photo and get a different variation of this photo. And then also I can get kind of this more targeted ways of editing, in which I actually specifically say, okay, here's a photo. I freeze some part, in this case faces, kind of in this photo, and then I want to change the backgrounds in a consistent way, in a way that I want to do it. And by the way, the reason why there is Trevor Noah here is that actually this work was triggered by a Trevor Noah piece about deepfakes, and we wanted to show that this technology indeed is already here. And the question is what can you do to protect against that? Okay, so this is the use case, and of course the use case we will focus on is the third one. So what we are trying to do here is to develop an immunization against this diffusion model-based model-based editing. Okay, so normally if I take a photo from a social media, I can kind of edit it into whatever other kind of photo I want to do using diffusion models by just putting the mask and then feeding the prompt. So what I would like to do is I would like to have a way to immunize my models. Essentially, I would like to, before I upload my model online, my image online, I would like to be able to put some tint on this, something imperceptible to me, but something that once the image is immunized and someone tries to use the diffusion model to modify it, it will end up being very unrealistic. Actually, it will destroy the ability of this diffusion model to actually provide a realistic edit. Okay, so that's what we want to do. And the key, probably many of you already guessed it, like the key tool here is to use adversarial perturbation. So how do we do that? Well, the first approach is essentially something we call encoder attack. So for that, let me just first walk you very quickly through how a latent diffusion model works. So essentially, it takes the input image, it kind of transforms it via encoder into a latent representation. There is a diffusion process happening in the latent representation. And then there is this kind of text encoding that kind of adds this latent vector responding to the desired context. And these are mixed together. And then there is a denoised process done, which gets you the denoised latent representations that again gets decoded into the new image. So kind of that's kind of roughly how this whole process works. And now when we talk about encoder attack, what we really try to do, we just try to attack the first piece. So essentially we try to attack the disrupt, like we try to modify the input image X so that its encoding Z is not the actual encoding that it should be, but some kind of modified version of it. So essentially, we make this encoding of this image be something else. And this way we hope to disrupt the whole, subsequent process of editing. Okay, so that's the idea. So you find an adversarial perturbation that makes essentially this encoder kind of encode this input image wrongly. Okay, so how does it work? Well, here is the example. So if this is my original image and I got prompt a black cow on the beach, if I just do it standardly, I will get something like this, which is pretty good. But if I actually apply it to an immunized photo, I will get something completely different and realistic. Similarly, I have this cat, I have it playing poker. If I do it with this, generative model, that's what I get. And here is, by the way, my student Hadi, who is the first author of this paper, and Trevor Noah, they actually met and they took a selfie. And now Hadi wants to, invent the whole life of, Trevor and him being best buddies. So he can do like two men attending a wedding, and normally that's the picture you would get, which is kind of quite convincing. But if this photo was immunized, that's what you would get. So everything works as desired here. However, it turns out that not always things work perfectly with encoder attacks. So here's an example. If you wanted to actually say that we are on the plane, well, this is a very convincing image of being on the plane. But actually, even after immunization, it's kind of essentially the context is too strong, and the model still ends up finding a quite realistic image. So the question is now, how do you provide a stronger approach? And this is where essentially something called diffusion attack comes in. So in diffusion attack, we kind of don't only try to diffuse undermine the immediate encoding step. We actually try to undermine the whole diffusion step. So essentially, we figure out how to modify the image so that if I put it through this whole diffusion process, I actually end up with essentially something different than essentially like some fixed, let's say just white noise image. Okay, so this is kind of much more challenging because you essentially have to backprop through the whole diffusion process, but it can be done with some engineering. And the question is, did it work? And yeah, the answer is it did work, because now the images you get are actually like indeed, much less realistic. So that's kind of how our solution works. But is that a complete solution? It definitely isn't. We really mean it as just a proof of concept and conversation starters. For now, you would need to kind of figure out how to make this immunization robust. So essentially, how to make it robust to tampering with the image. So if I just take a part of the image, will the immunization still work? Or if I kind of add some noise, will it work, and so on? And of course, you also would want this to work against many different generative ML models, not just a particular type of a diffusion model. So that's one thing. And of course, you can lean on here on the lot of work in robust adversarial examples. And also, the idea here is that actually the way we would think of deploying it is that we would want the developers of these models to work with us to help us design such an immunization. So they could make sure that actually the model is vulnerable to a particular immunization, vulnerable in quotes, because this is this point desired behavior, and they can also make sure there is a forward and backward compatibility as well of different things. So, and you can also remember that you can always in the end just simply Photoshop the image or use a rogue model, or but this is all about friction. Like, just you don't want this to be to find too fast. Okay, so that's all I have to say essentially. So let me just kind of summarize. Yes. There were just like okay, I think someone is not muted. So essentially, we have seen like two types of defenses against data-driven manipulation. One of them is just this new perspective on like how to think about backdoor attacks and how to detect them, and kind of we leverage data models to operationalize this view. And the other one is to kind of protect ourselves against the diffusion model-based image editing, in which you kind of use adversarial perturbation as an immunization against being possible to edit with these models. And of course, this was only the first step towards mitigating this really societal risk here. And I think really our community should think much more, what are the dangers that our technology enables here and how to mitigate them. Okay, that's all I have to say, and I'm happy to take questions. Thank you.
Thank you, Professor Madry. So we have time for one question, please. Any questions offline or online? Any question?
Hello, Professor. Well, I have a question here about I have a question about the mentioned defense against the AI generated contents of the facial images. So what I have seen in your talk is about to use the protective features to protect the possible malicious manipulation of people. But so if I have like so if I have an arbitrary image and a prompt, so how will I possibly recognize like what kind of prompt is malicious to our society, and what kind of images should be protected or not, or if and if hackers can directly use this kind of features to attack those AI to attack those AI generated models to fool the power of AIGC. So my first question is how to identify if a prompt or if an images should be protected, and the second one is how to mitigate the possible malicious use of this protective process. Thank you, Professor.
Yes, so that's a great question. So in some sense, like, we are sidestepping this question because we say, or we give the user before uploading the image anywhere that it can be accessed to protect, essentially say, I don't want any edits of that image. Like, I just won't block any editing of these images. So that's nice when the user can decide it, but you're right. It would be nice to have a complementary solution in which the companies running these models just say, look, this prompt, let's say, okay, this is clearly a prompt that would put the person in the image in a compromising situation. We don't allow that. Or you can say that, okay, we are not editing, images of politicians or some public figures, or maybe we allow some public figures. I don't know, like, just it is a kind of very good conversation. I don't know what are the answers, but I think we need to have this conversation and we need to come up with some solutions, like what is allowable or not. But this is like complementary to what we are doing. And you have also this interesting point about, okay, if our models are vulnerable to this kind of immunization, because we really are essentially like indeed like exploiting the vulnerability of the model, then can then hackers kind of use it to make the model edit things it's not supposed to? And that's a great question. And in some sense, I think this, this can be prevented. So in some sense, you can think about that this immunization will be something that is like a secret recipe that actually, if you know exact, kind of private key of how to trigger this, this vulnerability, you can do it. Otherwise, you don't. That might be the best way to do it. But you are right that there is a kind of a bit of always this tension that, okay, if I make my model vulnerable to something, it might be that it also will be vulnerable to things I don't want it to be vulnerable to. So that's all great questions. So I don't have answers, but I acknowledge that these are really, really good questions we should start thinking about as a society.
So thank you, Professor. Thank you for your amazing talk.
Hello, can you hear
Yeah.
me? Here is the on-site question. Yeah, please.
Yeah. Thank you, Madrid. Thank you, Professor Madrid. So
thank you. Bye.
Yeah, bye.
Okay. Okay, sorry. Okay.
So do I need to introduce the second keynote speaker?
Yeah. Okay. I will introduce. Okay. Yeah. Welcome our second talker about Dr. Sun. Dr. De-Qin Sun is a staff research scientist at Google, working on computer vision and machine learning. He was the postdoc fellowship at the Harvard University and was then a senior research scientist at NVIDIA before joining Google. And he served as the AC for CVPR, ECCV, BMVC, and the co-organizer for several workshops and tutorials at CVPR, ECCV SynGraph. He received the Palmi Young Research Awards in 2020 and the Lockett Higgins Prize at the CVPR 2020 and the Burst Paper Honored Mention Award at CVPR 2018 and the first prize in the Robust Optical Flow Competition at CVPR 2018 and ECCV 2020. So welcome Dr. Sun for his talk. Yeah.
Okay, yeah, sorry for the delay and thanks for the introduction. I'm very glad to be here to talk about our work on pyramid adversarial training. It's collaboration work with my colleagues at Google, especially Charles Herman and Kyle Sargent, who are the main drivers for this project. And as you can see, this is published work at last year's.
I'm sorry. We cannot see the screen.
You cannot hear?
We cannot see the screen.
Oh, you cannot see the screen. Can now?
Yeah, that's great. Thank you.
Okay.
Okay, cool. Yeah, let's continue. So as you can see, this is published in last year's CVPR, but I'm very glad the organizers give us this opportunity to discuss this work in detail. So our question is, can we improve both the clean accuracy and the robustness? So for here is we are interested in image classification on ImageNet. By clean accuracy, we mean the performance on the in-distribution data. For example, the validation set for the ImageNet. And for robustness, we mean the auto-distribution performance on the more corrupted version. For example, ImageNet A or corrupted or rendition or sketch or serialized version, which are more different from the training distribution. And also more specifically, we are interested in the vision transformer, which has been setting state-of-the-art for many vision tasks and has also been shown to be more robust than convolutional neural networks. And one observation for vision transformer is it usually depends on strong augmentation and regularization to make good performance. For example, random augment, stochastic depth, or dropout. And so in this work, we are interested in exploring also stronger form of augmentation, that is adversarial training. But if you look at the literature for adversarial training, usually people found there's a trade-off between the clean accuracy and the robustness performance. Usually, for example, what people found is when you improve the robustness, the accuracy on the clean set began to drop. The only exception is this very nice work, AdProp, or the adversarial examples improve image recognition. What the author shows is for convolutional neural networks, with a carefully designed split batch norm, you can improve both the clean and the robustness. And this actually gave us a great inspiration to explore for vision transformer, a new architecture for computer vision. But first, I will briefly introduce the basics of adversarial examples and adversarial training. So what are adversarial attacks? You may see these examples many times. So for pre-trained classifier, for example, if it can give this panda example, for the clean image, it can most competently classify the example as panda. But if we just add like a per pixel perturbation, which visually doesn't seem to affect the image, but if you give it to the classifier, it will very confidently misclassified as another class, like given in this example. And the perturbation is taught to fool the classifiers. So how can we do that? So we can randomly pick up a target label T, and then we can learn the perturbation so that when we add the perturbation to the input example, the model will be fooled to predict this is class T instead of the real label. And how does the training work? Let's see the standard training. We have the data. We do augmentation. We train on the augmented data. But for adversarial training, there are two branches. Besides the normal training, which we call it the clean loss or clean branch, we also have the adversarial loss or adversarial branch. So for this branch, we have the learned perturbation during training. And this branch will be learned on the adversarial examples. So mathematically, we can also see it. So for the normal training, the loss will be on the augmented data x tilde, and also plus the regularization on the network parameter theta. And for the adversarial training, we have an additional branch. So here, delta will be the learned perturbation, and x tilde plus delta will be the perturbed image. And we have this clean branch, which is the same as the normal training. And on the other hand, we have the adversarial training branch, which are learned on the adversarial examples. And if we just examine the training loss, this actually gives some sense why you improve the robustness by adding this additional adversarial branch. You gain performance better on the robustness benchmark, but because you cannot like disturb your original clean training objective, you tend to lose on the clean accuracy. And so this is kind of the intuition. But surprisingly, we found like when we apply standard adversarial training on vision transformer, for example, pixel-wise perturbation, we have performance improved both on the clean side and also on the robustness. So here is the clean side validation, and these are three robustness benchmark. And as we can see, these are visualizations of the perturbation, which we magnify the magnitude so that you can see the structure of the attack. But when you add it to the image, you can see still the image is very similar to the input. And one observation is we see is if we increase the amount of adversarial attack, for example, for this dog example, the perturbed image, the signals of the dog began to be distorted. And for such cases, we found such a stronger attack began to make the performance worse. For example, for this graph, this is on the clean accuracy. So here on this point is there's no adversarial attack. And when we began to add adversarial attack, the performance began to improve. But when we increase it stronger, the performance drops. And similarly for the robustness performance, first improve and then drop. Because the signal can become distorted in the original input. And so our intuition is, can we still make big changes to the image, but without distorting the signal content? And for example, we can make like a big change to the overall brightness. And in this case, you can see the magnitude of change is still big, but the signal content is still there. And that's the main motivation. So we can use more structured or less flexible attack at a higher magnitude. And we can increase the noise and still preserve the signal. But how can we structure the attack? And specifically for vision transformer, the natural choice actually is simple because the vision transformer will partition the image into blocks. We can just perturb the block individually. And more to generalize this idea, we can perturb the image at multiple scales. So at the pixel level, at the block level, or even at bigger level. And this constitutes, we call it a pyramid adversarial training, or pyramid AT. We can see we can learn the perturbation at different scale, bigger scale, a small, intermediate, and pixel level perturbation. And we can sum the three perturbations at different scale and add it to the input image, which will fool the classifier by vision transformer. For this case, from Basenji to Bassoon. And mathematically, let's see how we can express this pyramid attack. So this will be the adversarial branch for the normal training. We will add the pixel-wise attack dealt to the augmented data. And for our pyramid attack, because we are constructing the attack at different levels, so we have a scale parameter S that represents the scale of the adversarial. And for each scale, we learn a perturbation pattern. And then we have a magnitude that control how much we let this perturbation to contribute to the overall perturbed image. And we can see in terms of performance, using the pyramid adversarial performance, we can attack the image at a larger scale, but still get better performance. For clean is we can see increased performance. And for robustness, the lower is better. There's also performance. And overall, if we see all the benchmarks, including both the clean and the adversarial evaluation, the performance is very consistent. Both strong performance on the clean evaluation and on the adversarial data sets. And it kind of set a new state of the art on 3 robustness benchmarks at the time of publication. This includes both training on the original ImageNet or using the original ImageNet 21K. The performance is very consistent. So one question you may have is adversarial critical? How about we just do random noise at the pixel level or at the pyramid level? How about their performance? And so for this application, we do say random pixel or random pyramid. We can see for random pixel, there's a adversarial pixel, the performance most for the adversarial pixel attack. So that shows like adversarial learning the perturbation is very critical. It's better than randomness. And the conclusion also holds if we first train the data, the model at the 256 and then fine tuning at a larger resolution, which gives a kind of better performance. So this is just the first pre-training on the 1K example, then 21K, and then fine tune on the 1K example. And still the conclusion also holds both from the pre-training and the later fine tuning. Although we developed this technique for vision transformers, we found it actually works for other architectural backbones. For example, different versions of ResNet, the MLP mixer or discrete VIT, which is more the vision transformer family. But for convolution neural networks, we also see the improvement. And to better understand the pyramid attack, we can visualize the attention for the model trained. The baseline is without any adversarial attack. And this is the pixel-wise attack. This is the pyramid attack. We can see in terms of attention, the model trained with the pyramid adversarial attention attack tend to have more spread attention over the at different global scale. And if we can see some specific examples, for example, the baseline or the pixel attack trained model, they tend to maybe concentrate on a particular salient part of the object, say just the head of the dog or the beak of the bird. But for the pyramid attack, it tends to spread its attention to different parts. Say for the dog, it's not just the head, it could be the leg, and for the bird, it's the body. And by paying more attention to the global perspective, pyramid adversarial attack gets a better performance. And also to understand its behavior, we can look at it from the frequency perspective. For example, this is the frequency or natural images, which tend to concentrate on the low frequency part. And if we do random pixel noise, that will be uniformly spread over the whole frequency domain. And for random pixel, it's more concentrated on the low frequency part. And when we do adversarial tag, compare with the random pixel, the adversarial pixel tend to concentrate more towards the low frequency. But for the adversarial pixel, the amplification towards the low frequency part is more significant. You can see the most concentration is on the low frequency part. And we can also examine the performance in terms of the robustness to low frequency noise. The experiment here is we will add noise or the fixed norm, but at different, we cut off the frequency. So at the starting point, there is the low pass, it will, no noise will be passed. And then we gradually increase the threshold for the low pass, so more noise will be added to the image. And we can see the performance for all three models, the baseline, pixel attack, and the pyramid attack model. They both drop. But for the pyramid adversarial trained, like the blue curve, the performance degradation is more graceful than the other two models, especially at this low frequency part. Another observation or technical detail is we found the drop-off parameters affect the trade-off. So in this paper, we proposed the matched dropout and stochastic depth. That means for the clean branch and the adversarial branch, we will use the same parameter for dropout and the stochastic depth. We found it improves both the in-distribution and auto distribution performance. So what people usually do is for the adversarial branch, people tend to use the evaluation mode. That is, you use the full model. So that the model at the adversarial branch will be exactly the same as when you apply it to the inference mode. But we found if we use the matched, let the clean and adversarial branch use the same parameter for dropout and stochastic depth, the performance improves for both the clean and adversarial performance. And if we do not use the matched dropout, we can see even stronger performance on the robustness benchmarks, but performance will drop on the clean side. So that's a trade-off provided by this matched dropout. We also found random augmentation also matters. For example, we do the experiment on the VIT tiny model. We found, so for random augmentation with different magnitude, say here 0.1 is a lower augmentation or smaller magnitude than the 0.4, which is default for the B16. We can see here very interesting with the strong augmentation. And pixel adversarial training doesn't improve the clean performance, but it improves the robustness performance. But if we use a weaker random augmentation, and in this situation, the pixel adversarial training will improve both the clean performance and the robustness performance. And by comparison, if we evaluate the pyramid adversarial training, it's tend to perform more robustly for both lower magnitude or larger magnitude for the random augmentation. But the main message is the random augmentation and the pyramid adversarial training, they both augment the data. There seems to be some trade-off, and these two should be tuned together instead of first fixing the random augmentation. And if you just tune the adversarial training, you may have different conclusions depending on what random augmentation you use. For example, for the pixel with the tiny. And to also better understand the adversarial training, we can also visualize the pixel attack. And so for model train the baseline without adversarial training, with pixel level adversarial training or pyramid level, we can learn the perturbations that will break down the model. And we can see for the baseline, very small amount of noise can basically fool the classifier. But for pixel level, it's actually the most robust against the pixel level attack. It's even stronger than pyramid because the pyramid is not, it will attend both the global and the pixel-wise perturbation. It's not as strong as the pixel-wise adversarial training. But if we look at the overall like a pyramid attack, that will cause the classifier to fail for model trained by pyramid AT. We can see at the pixel level, the attack is very structured and kind of strong. We need very strong to make the model fail. So compared with the previous pyramid attack, you can see the image can be perturbed to a much larger extent before the model breaks down. And so some take-home message of why should I be excited about this work. So for applications, we show like a very simple technique that will work well in practice. And it's very simple to try out. And for research, there are actually a lot of room to improve. For example, we introduced one way to structure the adversarial training. So there are many different ways we can structure the adversarial training. And also, there's no free lunch. So the price we pay for the adversarial training is we need to pay longer training time. But although the inference time is still the same, but it's a very great research value to speed up the training process so that we can do more experiments and improve the performance. It's also interesting to integrate this adversarial training with other forms of pre-training, for example, self-supervised training. And also, as we have seen, there's a very delicate balance between random augmentation and adversarial training. It's also worthwhile to further investigating the relationship. That's all for my talk. Thank you for your attention.
Okay, thanks for the talk, and we can have a quick question. Yeah, any questions? Okay, if not, if you have any other details, you can,
Yeah, feel free to talk with me offline.
Yeah. So let's go to the next talk. Yeah, wait a minute.
Okay, thank you, Dr. Deching, for your amazing talk. So I will have a very brief introduction to our third speaker. Our third speaker is Professor Bolli, and Professor Bolli is an assistant professor in the computer science department at UIUC. She is on the advisory board of the Center for Artificial Intelligence Innovation at Illinois, and she is a member of the Information Trust Institute. She's also affiliated with several research centers aiming to broaden the research collaboration and bridge different communities, such as the Advanced Digital Science Center, the Center for Cognitive Computer System Research, and the Quantum Information Science and Technology Center. She also serves in the Accelerated Learning and Engineering Research Training Program. Her research focuses on trustworthy machine learning with an emphasis on robustness, privacy, generalization, and their interconnections. So thank you, Professor Bolli.
Hello, thank you everyone. Thank you for the nice introduction. So it's a great honor for me to share some of our research on trustworthy machine learning, especially on the certifiable trustworthy machine learning, considering different aspects, including robustness, privacy, generalization, and potentially their underlying connections. So first of all, as we can see before, that basically different machine learning models and techniques have been used in various aspects of our daily life, including autonomous vehicles, the large language models, face recognition systems, etc. However, we can also see that these powerful techniques have also brought us a lot of security and privacy concerns, including different accidents caused by autonomous vehicles over the years. And the output of large language models could be biased, could leak sensitive private information. And similarly, for the face recognition systems, different attacks have been generated even in real world, which has raised a lot of concerns, including misarrest. So we can see that even though, can you hear? Okay, so even though we have a powerful machine learning techniques recently, a typical machine learner still have a very hard life considering and generating the trustworthy machine learning systems. And there are even reports predicting that 2023 could be a security nightmare due to the malicious AI attacks. And building such trustworthy machine learning systems are very important for large infrastructures, including power grid, water networks, transportation networks, etc. And even just in 2023, in order to mitigate such potential risks and building up the trustworthy machine learning and AI systems, the White House has taken the agenda and published the blueprint for AI bills of rights, emphasizing the several important aspects of trustworthy machine learning, including robustness, fairness, privacy, explanation, and human in the loop. So before we dig into some potential solutions to the trustworthiness for AI and machine learning systems, let's take one step back to see what's one fundamental reasons and the causal reasoning for such trustworthiness problems in machine learning systems. So as we all know, like in traditional machine learning systems, we usually assume that the training and testing data are drawn from similar or even the same distribution. Therefore, we can train on one and test on the other. However, in practice, we can see usually either the training distribution can be manipulated, leading to potential poisoning attacks and backdoor attacks, etc. Or the testing distribution can be manipulated as well, leading to the well-known adversarial attacks and generalization issues. And I would say such a trustworthiness gap itself potentially lead to different trustworthiness problems we have seen so far. And therefore, in our lab, we mainly focus on designing the robust, private, and generalizable machine learning paradigms for real-world applications with guarantees, with the central goal of closing such a trustworthiness gap, as we mentioned before, which has formed at the center of different aspects of trustworthy machine learning. For instance, we can see from the robustness perspective, we're exactly trying to deal with, as we mentioned before, the adversarial manipulation for either the training or testing distribution, and their follow-up by developing different certified defense and knowledge-enabled logical reasoning defense approaches against those potential threats. And we'll give a little bit more information later regarding the defenses. And similarly, from the privacy perspective, we're exactly trying to minimize the output distribution distance given the sensitive information in the training to protect them. And similarly, from the generalization perspective, we're exactly trying to deal with the natural distribution shift compared with the adversarial manipulation, as in the robustness case. So I would say not only for each individual pillars here, but also their underlying connections are very important as well. For instance, we have been able to prove that given the Epsilon delta differentially private model, we can represent the certified robustness of the model as a function of the Epsilon delta itself. And similarly, under mild conditions, we can prove that the robustness and generalization are bidirectional indicators for each other. So I think these types of underlying connections are very important to help us get insightful understanding of the overall holistic view of trustworthy machine learning and actually help us to avoid reinvent the wheels, to help leverage the advances of one perspective to help the other. And in this talk, I'll mainly focus on robustness, but happy to take questions and discussion for other aspects on the line connections as well. So before we go into robustness, let's look at some interesting examples to see what is actually robustness in practice we talk about here and how we can certify it and why we need to certify it. So basically here, I believe many of you have seen these types of physical attacks like in the rote for the physical adversarial science. And the similar attacks can be performed for other domains like medical data, etc. But not only for image domain, but also for different NLP domain, including, say, here, the sentiment classification. It's very possible to just change one word, which to human, the sentiment still preserve the same, then it will fool the model. So here is a large evaluation against the large language model. Here is a GPT-4 to show that even the powerful model such as GPT-4 can be easily fooled by these types of adversarial attacks in the evasion as an evasion attack. And similarly, we can leverage the in-context learning by adding so-called the backdoors in the demonstration to easily fool the model and then change the sentiment or change certain predictions. And not only for the sentiment level, but also for the ethics. For example, here, very interestingly, we find that for any immoral behaviors, if you add a sentence, a word, actually, say unsuccessful behind it, and all the model, including here the GPT-4, can misrecognize such immoral behavior to be moral. So this could be very dangerous and lead to potential concerns in real world. And in addition to these basic examples here, next, I want to give a holistic view of the potential trustworthiness problems for large language models currently, because everyone is interested in these types of evaluation. And then we'll go to one fundamental framework to defend and provide certification for such against such attacks. So basically here, when we say trustworthiness, there are a lot of perspectives and criteria we talk about currently. So I would say, based on our summarization, we categorize the trustworthiness for especially language models and image domains into these following perspectives, including toxicity, stereotypes, bias, and adversarial robustness, out of domain like OOD robustness, robustness for adversarial demonstrations, and privacy, ethics, and fairness. And from here, I want to give some quick examples and show our recent findings. I think could be very helpful to many of the audience. So here, first of all, from the toxicity and the stereotype bias perspective, we can see that very interestingly, even just given the benign system prompt, it's possible to extract the model to output the toxic content for GPT-4 without any challenges or without any like system prompt level manipulation. And similarly, we find that it's possible to add a stereotype bias statement and then ask the model to be agreed with it to output the bias result. And here, as a quick summary, the observation is that compared with the language models without fine-tuning or RHF, the GPT models, including 3.5 and 4, have significantly reduced the toxicity in generation. But whenever there is an adversarial or jailbreaking prompt, the toxicity level can be improved into 100%, which is quite dangerous. And then the GPT-4 can be more vulnerable, surprisingly, because it follows the instructions better, so it will be more vulnerable against these types of jailbreaking system prompt, etc. So this shows that this level of even very like currently so-called superhuman power intelligence like GPT models still have a lot of trustworthiness concerns. And in addition to the toxicity and stereotype, I want to give some more examples here like including the robustness. For instance, as we mentioned before, it's easy to replace one word like experienced to skilled, and then the sentiment can be flipped. And then it's possible to change the style of a sentence, say change a normal style to be a Shakespeare style or other styles, and then the model will completely fail to recognize the sentiment of the or other NLI tasks for the sentence itself. And then it's possible to add backdoor demonstrations during training and still generate whatever adversarial targeted result you want. And the quick summary here or observation we got here is that although on standard benchmarks like the ADV GRU, the GPT-4 can suppress the current baseline models, still it could be very vulnerable against new types of or more challenging adversarial attacks by, say, transferring the attacks from the smaller autoregressive model, such as Alpaca 7B, to current GPT-4, which achieve very high success rate, like 89% attack success rate. So basically, this shows that still the models are very vulnerable whenever we do a little bit adaptive attacks against this. And next, we'll discuss why, how we can defend against it in a little bit later. And similarly, not only in image, but also in the NLP domain, it's very easy to extract the model for private sensitive information, such as private email here and the like a PI personalized sensitive information. For example, here the observation is that the GPT models can easily leak private sensitive information, such as email address. And if you provide a little bit more content, for example, the email domain or some other contacts, then the information leakage can be significantly improved. And it can not only leak the sensitive training data, but also the private information during conversations. Overall, like GPT-4 is more robust than 3.5 in terms of protecting the sensitive information, but still it can leak almost all the private information under the adversarial system or user prompts. And surprisingly interesting one phenomenon is that for social security number, for instance, no matter what condition you give, the model will not leak it, which is very interesting and could be highly related to the instruction fine-tuning for these types of models to specifically protect very sensitive information such as SSN. And finally, you can see the models actually have different understandings in understand the privacy related words and privacy events. So I will not go to detail about other perspectives, but here as a quick summary, we can see that different attacks from image, NLP, and multimodal perspectives. So the good news is that there are a lot of defense or detection approaches which have been proposed to defend against such attacks. But the bad news is that there is always traditional security cat and mouse game, where you have a new attack and you have a new defense, and then you have a new adaptive attack again, which triggered us to show that providing certain certification for robustness is very important. For instance, here, we can see that the intuition of such robustness certification is to give up certain % accuracy of the model under certain capability of attacker, meaning that there will be no further decrease of the model accuracy as long as the attack satisfies certain constraints. So we don't need to worry about future attack strategies or future adaptive attacks. So that's very important for us to get a certification or verification. And slightly more formally, here in terms of robust certification, we exactly want to get a lower bound of the model accuracy under certain attack constraints. So here, to be more formally here, we can see that we exactly want to optimize the upper bound of the model under the worst case attack, which is the delta here. So basically, we want to maximize the model parameterized by theta over the perturbation delta. And such perturbation could be any transformation, including the well-known like LP-norm based additive perturbation, or other types of transformation like rotation or colorization, etc. And under the constraint that C represent any distance functions. So basically, the constraint is that the perturbed instance and the original instance X need to be smaller than some distance constraint. So basically, we want to get the upper bound of the loss here, and then by 1 minus it, we'll get the lower bound of the model accuracy itself. But as we can see, since say a neural network is a non-convex, non-concave function, and optimizing such a max loss is NP-complete, which have been proved. So we have to use different approximation approaches to approximate such upper lower bound. And concretely, as we can see, in order to approximate this upper bound, take this instance as an example, that X is a point and this weird shape is a perturbation region that we want to optimize over it. And we can see the first direct way to provide the certification is that we can use different linear constraints to characterize the the constraints here, and then we can optimize over it by form the problem as a LP or mixed integer linear programming to solve it. But this is very expensive, and so far we can see these types of certification can only scale up to around 400 neurons each. And then we can do further relaxation by putting this weird shape into a more regularized shape to further relax it, so that we can see here we will have a lot of false positive, but will not have false negative in this case, which is acceptable in from the security perspective, so that we can use different relaxations to optimize over this regular shape. And furthermore, we can provide the probabilistic approaches by sampling points in this regular shape. So there are a lot of more details here, but the good news is that we don't need to worry too much detail here, and we have provided a unified toolbox which has integrated all kinds of certification and the robust training method, and you can call it and provide certification for any deep neural networks. So far we can see this is great. The certification can provide rigorous and robustness certification for any DNN models. But on the other hand, we can see, as we mentioned, it is also expensive and provide loose certification bounds in many cases. So let's take a brief look to see how loose such certification could be, and what's the progress we have made so far over the years. So we can see that actually, unfortunately, since 2018, the certified robustness have been provided for deep neural networks. The improvement have not been much over the years. So here on the x-axis, we show the best results in each year over different conferences and papers and articles. And the y shows the certified robustness. And we can see the top two lines represent the MNIST under different radius, and the middle two lines are for CVPR and bottom for ImageNet. And we can see the improvement is not that significant over the years, especially for like data set like CVPR and ImageNet. The performance of the certified robustness is far away from being useful. So we can see that the certified robustness for purely data-driven approaches like deep neural networks, although a lot of effort have been made for this area, I can promise you, still such certification has reached a bottleneck, and the new information and the paradigm are really needed. And for instance, here in our group, we still maintain some state-of-art certification for some data set here based on purely data-driven models, such as neural networks. But this is far away from being useful, as we can see. So this shows that such purely data-driven models have reached a robustness bottleneck. And we do need to integrate some additional information, such as knowledge and experience from human perspective, to further improve the certification for machine learning paradigms. So the intuition is that, can we integrate data-driven models with some knowledge-enabled logical reasoning? And the reason is, for instance, take the stop sign here as an example, that we can see if we, as a human, we take a look at it, we actually see lots of information, such as the octagon shape, such as the stop word, and the size mostly red, and some useless information, such as the stickers here. So we can see, because of this, as a human, we can do a pretty good job to recognize this stop sign based on the knowledge and the extraordinary information for reasoning. So this gives us a hint on whether we can integrate the powerful data-driven models, which can make lots of mistakes, with the knowledge in logical reasoning to achieve both high accuracy and certified robustness. So here, this is a high-level intuition for such a framework. So basically, given the real-world data, and we can optimize it for some models, and here is what we usually do for the data-driven learning. And then, since we have lots of real-world knowledge, we can encode the real-world knowledge and use it to represent the relationships among different data-driven models and provide the knowledge-enabled logical reasoning. And here we call it learning and reasoning framework. And the goal is to integrate the reasoning component to any particular data-driven models that we have currently. So take a simple example as still use the stop sign as an example. We can see that here, given the input, we can train a bunch of models, including a main model which predicts the row sign, and is octagon shape model to predict whether the input is of octagon shape, and the other properties. And then we know there are some real world knowledge, such as a stop sign should be of an octagon shape, and therefore we can represent the knowledge as a first order logical rules, and then embed such first order logical rules into certain probabilistic graphical models, such as Markov logic nets, etc. And then therefore we can have this end-to-end prediction and the correction for the reasoning component. So the intuition is that given a single input, if we directly input it to a single neural network model, because the model have very high uncertainty, we can see it will be very hard to provide tight certification for neural network itself. But with the reasoning component as a recorrection for the prediction of the models, we can see that the confidence will be significantly improved due to the knowledge integration, and then we can provide a tighter certification for the model itself. And next, based on this simple example, we can abstract this framework as a learning reasoning framework with the data-driven models, which we can train different neural networks, and the reasoning component where we can train, say, Markov logic nets or Bayesian nets or probabilistic circuits, etc. And there are several benefits for such a framework. For instance, on the high level, it's very hard to attack such models, like basically every model in the learning component, but still preserve their logical relationships. And there are several other key advantages. For instance, with the data-driven model, learning model component, we can learn effective models with good representation power. And we can also leverage the reasoning component to support reasoning and correct the malicious or fault model predictions. And one key property is that the knowledge here doesn't need to be as comprehensive as a good old-fashioned AI, because here you can see we don't rely on the knowledge or the reasoning to make inference as the traditional symbolic AI. We just use it for like violation check or the robustness improvement. So even we don't have enough or good knowledge, our performance is at least as good as a single learning component. But if we have certain useful knowledge, then you can see both the binary accuracy and the robustness will be improved. And it also provides end-to-end prediction, robustness certification, and some explanation as a byproduct by looking at which types of rules are violated. So based on this, there are several interesting properties I will briefly mention, but I will not have time to go into detail for it. So basically with this end-to-end framework, it's possible to provide the certification for it by solving the upper-lower bound for the reasoning component. And we will show quickly that the certified robustness of such a learning reasoning framework actually is significantly improved, like around 30%-ish compared with a single learning model like neural network, which is quite significant. Recall the line plot we shown before. For single data-driven models, like even 2 or 3% improvement for certified robustness is already quite significant. But here, with the reasoning, you can achieve like a 30-ish improvement. And second of all, it's possible to prove that this end-to-end framework is more robust than a single model, as long as the knowledge models make non-trivial contributions. And this is a sufficient condition, which is quite interesting. And finally, we can also make it quite scalable by adopting GCN to encode the knowledge and the reasoning structure here. So let me skip some results and look at some interesting applications of it, which can be applied to not only image classification, NLP tasks, generative models, and all kinds of various safe autonomies. So here we can see, what's this? Let me skip the result. So here we can see in terms of the animal classification. So basically, with the learning reasoning framework compared with all the state-of-art certification methods, we can see not only the binary accuracy is improved under the epsilon equal to 0, but also the certified robustness is significantly improved, especially on the large radius, as I mentioned, which is very important. And for certain NLP tasks, both the binary accuracy and the certified robustness got significantly improved. And not only for the classification of generic tasks, but also for generative models. For instance, here we can see if we can integrate the knowledge into a tree structure to guide the generation tasks. For instance, if without the knowledge integration, we can see on the right-hand side, if you just give this prompt to a diffusion model, you will generate something on the right-hand side, which is of high resolution, but not realistic, right? So in this case, integrating knowledge, including the standard common sense knowledge or the, like say, the causal relationship as one type of knowledge is very important to help the generation and generate this. In this example, we generate the safety critical scenarios for testing. And to extend this, it's possible to leverage the large language models and then give different descriptions of the safety critical scenarios and then map it to the code and automatically generate and evaluate the scenarios in color directly. So with this, I want to say the robustness, especially certified robustness, is quite important. And here I want to show some useful platforms for providing the certified robustness for different deep neural networks and certification for reinforcement learning, NLP tasks, different federated learning, distributed learning, and not only like robustness, but also other functionality like AI ethics and real-world autonomous driving safety testing, etc. So if you're interested, these platforms can help you to easily deploy and evaluate certain approaches and applications you have. So with that, I want to summarize my talk, which shows that the trustworthy machine learning is indeed one key enabler for many real-world applications, yet it's largely remained unsolved. And we have seen that it's possible to define some adversarial constraints and certification criteria to provide certification for models. But based on purely data-driven models, we can see it's kind of like the puzzles in different places. And as long as we can leverage the knowledge to put them together, we can achieve better both accuracy and robustness and other interesting good trustworthiness properties. And we show that such a learning and reasoning framework can be generalized to different applications and perform certified robustness and other properties. So yeah, with that, I'll end my talk and happy to take questions. Thank you.
Thank you, Professor. We can have one question here. Any question online or offline?
Any questions? Any online questions? I think on site there's no questions.
Okay. Thank you, Professor Bolli. Thank you. So you can introduce the next speaker.
Okay. So thanks. Let's welcome the set talk from the Professor Chihang Xie. Professor Chihang Xie is an assistant professor at the University of California, Santa Cruz. His research interest lies at the intersection of computer vision and machine learning, with the goal of building human-level computer vision systems. He is particularly interested in sequencing model performance under distribution safety and developing deep representation learning with minimal supervision. So welcome, Professor Xie. Yeah.
Okay. Can you hear me? Oh, okay. Oh, yeah. Oh. Also, actually, can you hear me? Or Zoom?
Yeah.
Yeah, you can.
Okay.
Much. Oh, okay. Good. Try again.
So today I'm going to talk something a little bit different from the typical robustness research. I'm specifically we're talking about inverse scaling law for clip training, and I will explain why this will be closely related to the adversarial or robustness research in general. So first, CLIP is basically the first foundation model that connect the image and text. And the training work for the CLIP is pretty conceptual simple. So basically, you get some text input, you get some image input. Text input goes through the text encoder, image goes through the image encoder. And then because your input is basically some image text pair, right? So you get them be related, they are treated as positive samples. And for different pairs, like say image pair with a different text, that basically treated as negative samples. And then you can base on this contrastive idea to train these models at scale. Very simple idea, right? So, but pretty powerful. And at the inference stage, something pretty amazing by the CLIP model is that actually they can do the zero-shot inference. At the inference stage, basically you just get some prompts. This is a photo of a cat, a dog, and goes through text encoder and send images through the image encoder. Then you just find like which text message get the best match with the image encoder, and then give the output. So some background, like say why we want to study the clip model here is that, for example, like my previous work, like one in NeuralPhysics 2021, I compare the robustness between the vision transformer and the traditional CNNs. And you can see like for ImageNet, they behave pretty similar. But for the auto distributed robustness, they get like say for ImageNR, 2.7% improvement. For ImageNA, 5.9, and for the stylized ImageNet, they got 2.2 improvement. So at that stage, we're pretty excited about these results. And we later also get some follow-up this year, iClear. We started the robust CN. We make the CN be more robust, even more robust than the ConvNext. So at that time, like we're excited, but recently when we focus on the clip, and here is the clip results. So for ImageNet, they still compatible. But for the auto distributed robustness, you can see a pretty huge improvement, not just 5 points, 2 points, 3 points. It's more like a 50%, 70%. So that's a huge gap. So that's why we like say persuade my student to say, okay, we should start a clip and say how much more robust we can make, and whether we can like say design some super robust model to maybe solve the robustness problem. So a little bit background regarding the clip is that once like at the time of the OpenAI released the clip model, they actually do not fully open it. They just give us the inference code, some weights. You can do some toy model inference. Maybe that's still useful, like for a lot of applications, you can get a clip embedding, you can do some downstream tasks. But they didn't give the training code. And also their data set is in-house data set. They until today, they still like do not open it. And along the history of clip, basically 2 milestones has been made. The first is the open clip training code base. They released the full training and testing code of the clip, and that's a huge like say open source regarding the clip process. The second thing is the line data sets. Line data set basically they open source the 400 million image text file. That's a line for 400 million data set. And also they open source the line 2B data sets. And that's basically contains 2 billion and also like the superset is 5 billion data sets. So that's a lot of data. So now we have the code, we have the data, right? So that seems we can like say run clip by ourselves and do our own research. But the truth is that requires a lot of money, right? Because typically when you do the like say in the open clip, their code base, they like some even like say for some VIT small or basic experiment, they require 100 of GPUs and train for several days or several weeks. And also like say for their pretty huge model, like VIT huge or VIT large or VIT giant, they require thousands of GPUs, and that means a lot of money, right? As our academic lab or some small startup or individual researchers, we don't have that access to this huge amount of computations or have huge budget for running clip, right? So that's the main motivation of this work. We're trying to, like say, we still want to train pretty high performance clip model, but we want to train them with pretty limited resources. For example, originally, like say 1,000 GPUs, maybe now, like say train the scale-out clip model, can we just use 8 A100 GPUs? So that's our goal. So our work is largely inspired by the Flip, the fast clip training framework by Chemical for Meta. And their idea is also pretty simple. Originally, like say you do the contrast learning in the clip, you get an image, you get text, you contrast learn and to calculate loss, right? And there, I think last year. Yeah, last year they first published the MAE, the mask autoencoder work to do the self-supervised learning. The basic idea is that for the image, you're not necessary to input the full image. You just select a subset of patches. And that's pretty suitable for the VIT architecture, right? Because VIT architecture, you can randomly sample some patches and apply the self-attention to calculate their relationship and send to the as the output to do the contrast learning. And they, in that original work, they show that's pretty helpful for the learn our self-supervised learn work, MAE, and like say also do pretty good on imaging task, also some auto distribution tasks, and also benefits a lot of downstream tasks. And then this year, I think this is this year CVPR, they brought this idea to the clipper training. The same here, they show that rather than input the original image, you can just select a subset of patches and then do the contrast learning. For example, if you like say just sample 50% of your patches, you can accelerate training by 2 times, right? If you just select 25 or you're lower, you can accelerate your training more. So that's the idea we try to follow. But we, and here's some amazing results. You can see, like say, compared to the open clip results, they not only get faster, but also yield better performance. Because once you say only train with a subset of your image, you consume less memory, right? And then therefore, like say for the same GPU, you can probably double or make the batch size 4 times more. And in clip training or control in general, large batch size is a pretty important factor to contribute to high performance. So that's good. That's why this work basically, I would say, boosts the clip training a lot and make it more accessible to the research in general. And what we're trying to do next is say, yeah, here is just some additional results. The results are good, better accuracy, and faster training. And also, like say, one key point I would like to bring up here is that once you train with this reduced token, right, just 25% or 50% of your tokens, you need to do some unmasked fine tuning. That means your majority of training is done on the mask images, but later after you tune, you should tune a little bit with the image at a full resolution. And then that can basically improve, give you some additional improvements of your models. And for our experiments, we try to follow up their settings. We train with a small base, large model. We use a line for 400-minute data set, and we evaluate on the image at 1K. We pre-train for the 2.56 billion in image text file, and then fine tune on like say 128 million for the fine tuning. So you can see majority is done on the pre-training part with small images. Fine tuning is done a little bit, pretty light on the full resolution. So we want to do something more than just say do the random masking. But actually, we have a lot of ways to do the masking, right? For example, we can do the grid masking, and that's one strategy they test in the original Flip paper, and test on the original MAE paper, and that's not very good on the self-supervised learning. But we show that this is also good for clipper training. And also we can do the block mask, right? And where we just select our small block of your images and do the training. And actually, another thing we could do is that we can just directly resize the image. Rather than train the image at full resolution, we can first resize the image and do the training. And basically, here are the results. And first, I will just show for the random masking. Some interesting phenomena we see here is some inverse scaling. That means for larger models, you are able to train with larger mask ratio. That means the smaller tokens you can use. For example, like say with the same number of tokens, you can see the large is consistent better than the base, and base is consistent, almost consistent better than the small model. And also like that also can be interpreted as like say for the same performance drop, like say compared to the full resolution training baseline. Like say I set a goal as to say I can only allow the performance to drop by 1% or 2%. That means your large models enable you to train with fewer tokens. So that's a universal scale we summarize here. And that basically also applicable to the resize, block masking, and grid masking. You can see both basically for all these different masking methods, they all satisfy or almost satisfy this criteria about the inverse scaling. And also, like say, we compare this 4 different masking policies, and we can see that basically the resize give us the best performance. They can perform better than the random masking, grid masking, or block masking. And also, that's about the text, right? That's about image. And next, we can talk about, say, how to reduce the text. So first, like the same, for the original sentence, we can just do the truncation. That's by default, they apply in the clip training mode. We just select, say, the first 4 words. And also we can do the random masking, just select some random words for training. And also we can do the block masking, like say select our subset inside the original sentence, but the letter consecutive. The last thing we can do is that we can do the syntax masking. That means we just first, like we give the first priority to say we want to select the noun, and then select some adjective, and we have some preference sheet for like say which kind of words we want to select. So here are the 4 masking strategy for the text. Basically, here are the results. Something interesting we find that is like say, if we keep the text token more than 8, we didn't see a very substantial performance drop. Like say, you keep at 32, you keep at 16, you keep at 8. Basically, the performance will not change too much. Will not get some critical performance drop. But once you go beyond, say, less than 8, like 6 or 4, you can see the performance drop will go like say 1% or 2%, or around 3%, right? So, and the more severe situation is that say if we just keep 4 words, you can see even much worse results. So that's basically the observation for the text tokens. And also here the performance comparison, like say among these 4 text reduction strategies. And we can see that the syntax masking, say we give the highest preference to keep the nouns. Basically here the best performance. So to summarize, though like say we introduce several different masking strategy, we show which one works the best. But the high level message is the same. Say we can use, once we like say we use larger image encoders and larger text encoders, we can always say using smaller image and shorter text message for the training without causing some significant performance drop to your model. So that's the inverse scaling law that we're trying to reveal for the clip training in general. And next we'll show some interesting results. So here are we train the small model, base model, large model, and some huge model. And we basically, you can see the, like say, by keeping more tokens, the performance will go better, right? For different models, but also they will cost more compute. And some interesting phenomena, we can see that we can even train the larger model with better performance, even faster than some situation for you train small models. Some very interesting example you can see here is that for some version of VIT-B, they can do better than the VIT-S at the full resolution. The same applied for the large model and also for the huge model. So that means, like say, scaling is good, right? And everyone knows like scaling larger model will give you better performance. And it's not necessarily say scaling to the larger model will cost you more training budget to train them. And if you apply this inverse scaling law, that means train with larger models even can be trained faster than your small models at some specific situation. And also we do some experiment setting to say we want to train these models on just a single A100 machine, and we limit the time to say train with 2 days, 3 days, 4 days. And here are the results. So basically, you can see we basically name our model as a CLIPA, as a CLIP for academic. You can see for the B model, large model, we achieve pretty competitive performance on the ImageNet 1K data set, but with like say much less GPU hours. And also we test on those ImageNet V2, those OOD distribution, and also like say for image text retrieval, like on the Coco data set or the Flickr data set, you can see this all behave pretty competitive with some pretty good performance. And as I said, like here is a more visualization of say the GPU hours that were taken to train these models. For OpenClip, they needs a lot of budget, a lot of training hours, but for ours, we just cost pretty less. And curiously, like say, we talk about say for the inverse scaling law, we only like say apply on the pre-training stage, right? Like say pre-training we on this short sequence of the image and text, and then we fine tune with a full resolution, right? But actually, we show that the inverse scaling law can also be somewhat applied in the fine tuning stage. And here are the results. Here we specifically choose the random masking to say, even in the fine tuning state, you do not need to fine tune with the image as 224 by 224 with the text of 32. You can also like apply the masking rate even to 60% or 50%. You still will not hurt your performance, say more than 5.5%. So that means the inverse scaling law is also can accelerate your fine tuning process. And the same here, you should like say for the larger models, the larger masking ratio you could apply to save your computation. So basically, the last thing we do here is that we try to scale up the CLIP training. Here are some results. You can see we like say scale from the large model to the huge model, and also increase the training schedule of a huge model. We can keep improving, like get a better performance. So the 3 critical changes here, like first we switch from the larger model to huge model. We improve about 3%, and then from huge originally we train on the line 400-minute data set, right? Now we change it to the line 2B data sets. That improve another like 1%. And then we improve the pre-training schedule, that improves more. So basically that's how we do the scaling to yield consistent better performance. And here is just a table to more illustrate for the result we just talked about. And lastly, here is some, again, like some comparison to the training cost compared to the OpenClip. We can see that we use much less budget. Say with the model here it represents the dollars we need to train those models. we can train, like say within like say 10K budget, we can achieve pretty competitive results. And here is another thing here. If we keep scaling up, and the best thing we could achieve is the edge model on the data camp data sets, and we can achieve 81.8 accuracy. And recall that the previous, the best clip model released by only is 80.1. So basically we're like 1.7 percentage higher. And also we can also limit our training budget to be within the $15K for training those the best clip model so far. But I would like to say one key contribution for this high results is that we use the data camp data set. That's a new data set compared to the line 2B data set, and contains some more high quality image text pairs. So basically, that's a summarization. Compared to the OpenClip model, we are not only achieve higher performance, but also be more cost efficient. And the key takeaways. So first, we showed this inverse scaling law. That's the key foundation part to driven all these amazing results. That means scaling is good, large model is good, but not necessary to say large model means more computations, more training costs. That's not true. At least for the clip, that's not true. And also the token quality matters. And we can see that previously we show like among different masking strategies. For the image, we should do the resizing rather than do some masking policies. And for the text, we should choose the syntax knowledge rather than to say do the block masking or do the random masking. So this can improve the results a lot. So the last thing like is that once we can restrict the training costs to be pretty low, we can pretty aggressively scaling them to be large scale, but still within a very small budget, like 50K. Lastly, I want to thanks for my student Xianhan and Zeyu for making this amazing workup possible. And also I want to thanks the OpenFail for the funding and also the Google TPU resource for donating the TPU for this experiments. Our code is public available here, and our models are basically all open source. So you can download them to try for your different downstream tasks, or you can like say replicate our result if you have some free 100 GPUs. So that's all. Thanks.
So any questions? Yes, question.
Thank you for the nice talk. My name is Satyajit. So could you repeat like what is the drop in accuracy when you train the largest possible model with the best tokenization, best reduced sequence? Like what is the drop in accuracy compared to like full scale training?
Okay.
I guess you had that on some slide.
Yeah. So maybe we can look at this first. Like say first dropping more like say tokens definitely will give you lower results, right? But we set some threshold. I think practically but also that depends on which strategy you use. You can see here if you look at the resize curve here, like say if we drop the token number of token to just 50, resize only drops a little bit if you look at the large model, right? But for others, you can see you added the 50 here, the grid mask lost 2 points, the block mask lost more than 1 points. For the random masking also near 2 points, right? So the strategy indeed matters. Generally, we just find the resize is the best. And for our final version, like say the best model, I think for the VIT huge, we directly train with image resolution at 84 by 84. So that's a pretty small one. And to achieve those results. And also for the text, we always keep at the token size at 8, because as we show here, regardless of different taxing masking strategy, once you drop below 8, we think that's our critical threshold. You drop below 8, you will see some significant drops, regardless of
Text tokens or the image tokens?
Sorry?
This is for the text to.
Yeah, this is for text. Yeah. So yeah, for text, as I said, like we use a minimum of 8.
And which text reduction strategy?
Oh yeah, we use a syntax masking. You can see like say even for we choose at 8. You for syntax masking you get some performance improvement. So that means like the original text message may a little bit noisy, some or some unnecessary words like distract your attention in learning the text. So that's something happen here, and we choose the syntax masking. Yeah. Okay, thanks. You have okay.
Need to use his computer.
Do you have Zoom?
I have Zoom, not the link, and my email is now not working. Everything gets worse, so somebody may need to.
Do you have the
link,
Zoom link?
the Zoom link by hand.
His email is not working, so we have to type it by hand.
Yeah. Also, my computer is not, needs to be, the battery has died completely. It needs to be charged somewhere. I don't think I've ever had a day where so many things have gone wrong, and it's not even lunchtime yet.
No, just his email is not working with type by hand. So this is so weak. So your email is completely not working.
They're completely not working. My Apple iPhone is not working. This is a new iPhone from Apple that I bought only a few weeks ago. So I'm glad I never took a job at Apple when I had a chance.
Okay.这个评论有 short UI 来产生的，就是那个 tiny UI 就产生一个 short 的那个 version，然后看一下，看这网站看一下，看这里面。哦，对对，这里面short 的那个应该有 conference information copy。哦，这样，我记得 Zoom 是有 Zoom information，哦，或者是切入他的那个，在这里打入他的 email 就可以了。对，他 email copy invite link， 然后随便粘到那个。对，对，这个是一样的，这个跟那个 link 是一样的。你就在这里导入他的账号，用 link 的账号就可以了。哦，就是在这里。你刚才那个3里头。
Yeah. Can you put it in manually?
Yeah, I think so. It's okay.
Okay. So I should get started.
Yeah, you can start.
Do I need to press anything? No need for. Yeah. Okay, thanks. So let's just go straight into the talk. As I been saying, I guess I never had a morning where so many things have gone wrong with so much of my electronic equipment. And that's only one part of my morning. Okay, so talk is on robustness and beyond. And let's see, now this is not working. I've got to do this. I can't just press a button.
You can just
Click this one.
I just have to press harder.
Yeah.
Okay. So plan of the talk, first part is the introduction. Given by workshop talks, I may not be able to get beyond the introduction. And then there's a series of particular areas. I think, so let's get into this and I'll back. So I think robustness is a major problem for AI. I think deep nets are wonderful at exploiting biases of data sets. They seem to be human observers. This infamous thing from my perspective is saying that is really saying more about the limitations of deep nets than of humans. This is, it sort of makes it seem that AI is doing better, but this is really, I think, an artifact of the way we test AI algorithms on data that's very similar to the data they're trained on. And for people in my generation, it's nothing new. You can get an algorithm that does better than a human. They're called ideal observers. You just need to give the algorithm more information about the statistics of the data set it's going to be tested on. And every time you're going to beat a human observer easily, sometimes by orders of magnitude. So I think if we just do the standard testing on data that's similar than the ones we've been trained on, like 99% of the community probably does, I think we are, while making huge amounts of progress compared to where we were before deep nets, I think we're really fooling ourselves and thinking that we are solving the underlying problems. And robustness, the ability for algorithms to work well on data that may be similar to what they've been trained on, but it differs in small respects, is really important. So here is from one of my, Gupta and one of my students. This is a view QA system. You ask the color of the woman's dress to some highly sophisticated, wonderful state-of-the-art algorithm. It gets the right answer. You replace the tennis ball by a football or soccer ball, and the algorithm thinks the model prediction is white. The dress is white. Why? We have no idea. This is a deep network. They're uninterpretable. So, what can we do? We can give the deep network more data, right? But, okay, that's not really a great solution. I think this is really important issue. I was talking just before this talk, I met one of my ex-students who's now a high-level position in a well-known AI company which does practical work, and he's saying the way we test algorithms in the academic community is ridiculous. In his company or any other high-tech companies, if you want to test a computer vision system or any system at all, you test it far more rigorously than what we do with just a bunch of random samples. And it's sort of crazy because academics, we ought to be aiming at the next set of problems and not sort of effectively falling behind the high-tech companies because of the way we test our algorithms. So starting with the original attacks. So these were nice. The original attacks were these sort of, these sort of almost imperceptible modifications to images which cause deep networks to make mistakes. So this was interesting work. It was extended. You could attack almost anything. But what was happening was also that defenses were fairly quickly found. I mean, even the dumb defense of just sort of training your algorithm on the data that it got it wrong actually made sense, and this could be formulated nicely by Madri and others in terms of minimax training. That worked, okay. You could also find that the adversarial attacks could help improve the performance of deep nets on the original images, provided you paid attention to technical details like batch normalization, which Xiehang worked on, among others. And, you know, why was this? This was because, okay, these types of attacks meant that you were essentially giving the algorithms more data to train on with more annotations by effectively assuming that small changes to the image are going to correspond to the same objects. You've got more data to train on. This means your algorithm is going to work better. And it's still going to, but that's sort of the good news. But the bad news is only going to work better on images, which again are similar to the ones you've trained on. There's this huge space of images. You trained in this little set here. You've expanded it slightly by having this set of adversarial examiners, which are small perturbations, but there's lots of images out here and out here. It's, you know, and you're not going to work on those at all necessarily. So I think the real interesting challenges for me, and we worked on these things for several years, and Xiehang did really good work on it, was really the interesting challenges where they're not perceptible, they're perceptible, but a human vision, you know, human observer wouldn't have any trouble. And so this example of the woman playing tennis and the ball changes is one example of that. And so I guess the word attack, I mean, for this audience, it may well be clear, but I don't think of this as some malicious person trying to mess up your vision system. I mean, maybe that happens, but for me, it's a problem with the algorithms and the way they're tested. If something can be attacked, then it means that the algorithm successfully attacked. It means the algorithm isn't very good. It can work on this tiny little set of images that it's been trained and tested on, and that's probably enough to get it published in CVPR or major conference. But basically, it's not really a good algorithm. It should work for data over here too. And if it doesn't, that's a problem. So why does this happen? It's because the image set of images is really enormous. They're combinatorially complex. The idea that a finite size data set is enough to be representative of all images is just, you know, is just really unlikely, to give English understatement. So images are huge. You can try to test them with these sort of adversarial attacks. And for me, this is like testing out of domain, out of distribution, putting in occlusions, things like that. But this is only, I think, part of the way of dealing with the problem. So, you know, throwing occlusions, throwing changes to texture, etc. Right. So we ought to be testing algorithms on that. Now, can CNNs and transformers and the latest foundational models or anything work in these cases? Frankly, it's unclear. I mean, we don't know. We have to set up these performance benchmarks. We have to see if they can. Can they perform better than each other? Yeah, there were cases CNNs outperform transformers or transformers output CNNs. It really depends. You have to be very careful about how you adjust for the complexity of the models, the way they're trained, etc., like that. But from my view, basically, is I don't think the current models are going to be able to do this. I can be proved wrong. In some ways, I'd be happy if people did. But the reasons why I don't sort of believe it is I don't think that the models have the capabilities to do that. That's based on intuition. My intuition could well be wrong. It's been wrong many times, but unless my experience is, unless you've got an intuition or an understanding of why something can generalize to some new situation, it's probably not, however much data you throw at it. So can we modify these things? Maybe we can. We can modify the architectures in some ways. Will that be enough? How much do we need to modify them? I think, from my perspective again, is I think unless the networks become interpretable, this is going to start breaking down, because if you've got an interpretable system and it makes a mistake, we know we can identify where it makes a mistake, we can fix that part of it. This is basic engineering. This is how we design cars. This is how we design railway bridges. This is how we design airplanes. If something breaks, you have a system that if it breaks down, you know where it's going to break down. Okay, this is how high-tech AI companies do this, as my ex-student told me a few earlier, you really test enormously every possible thing that can happen. And that's not what we do in computer vision with just random testing. So an uninterpretable network breaks down, what do we do? Reviewers asked us in one of our recent papers, we said, okay, this network breaks down. Can you say why? We say, no, it's a deep network. How should we, if it breaks down, how the hell do we know why it's broken down? That's part of the problem. Okay, so now this is not working again. I'm pressing this down hard. It's not moving on. I have to touch it and press down. Yeah. Okay. So again, what should we do? Again, you can test with random samples from from out of distribution, et cetera, but I feel we need something more even more radical than that we should start testing for the worst cases over the whole set of images. If you want to test a scientific model, you do experimental testing on it. That's, to find out where it works, where it doesn't work. We don't do that in computer vision. We just test with random samples. We all should be moving to this type of thinking. And trust me, the companies do this, even if we academics do not. Okay. So how can you test over a huge set of images? Well, you imagine, there are too many. You can't just test everything at random. That's not enough. You can't do it systematically. That's not enough either. You have to think of better strategies. My group has done some work of this sort where you treat it as a game where with reinforcement learning. And so as the tester is like an adversary to the algorithm, they try and find out what stimuli the algorithm does not like. They do it by showing a stimuli, get the algorithm's response, then they, based on the response, they generate another stimuli, etc., and so on. This is not testing by random sampling. This is testing by essentially trying to pin down where the failures occur. And how am I doing for time? Because with everything I have breaking down, I'm not sure of it. Okay, keep track on me because I'm going to have to drop a lot of stuff I've prepared. And maybe I'll skim over things quickly. Particularly, there are things which are discussed in detail in some of the conference papers here. So if you're interested, you can go to the work done by my students. So first part is one thing called compositor robustness to exclusions by Zhu He et al., which is going to be at the main conference. So this is an algorithm for doing semantic segmentation on object parts. There are data sets like that, ImageNet parts, which Zhu He also constructed. And so you can train transformers or CNNs to perform this task. Okay. And the particular algorithm here is a form of a transformer. It has been modified in certain ways so that parts of the transformer are more understandable and more intuitive, at least to me and people in the group. Transformers, in this case, they have a property called self-attention, then they have cross-attention. What is cross-attention? Well, it's something borrowed from natural language processing. And if it's applied to semantic segmentation in just copying what it's done in NLP, it helps a bit, but it's not very insightful. It helps a bit because some of my students did it and you get good results, you get good state-of-the-art results, etc. What's more insightful is making a connection to k-means clustering, which is one of the older methods in computer vision. And that was done originally in this paper by published in ICCV last year. If you do that, the cross-attention is simply a clustering algorithm. You don't even need to call it a transformer. Somebody joked that we could have written a paper for transformers saying all you need is k-means. We should have done that. We didn't. Our papers published, I'm afraid, make them seem more like transformers than k-means. Why is that? We wanted them to get accepted by the current computer vision community, and having transformer in the title was better than saying, but having k-means in the title. So, okay, right, this is the world we live in. Here's very quick, which I'll skim over, but the point of it is if you take these k-mean transformer networks trained in a particular way and using k-means rather than just standard cross-attention borrowed from NLP, means you can actually understand what's going on in the network. And you can see that the network is effectively training to learn what I cynically called a magic feature, a feature that responds to a part anywhere within the part of the object. It's trained to do that. That's very nice, because if it wants to do inference, it can look at the image. It will now have a dictionary of part magic features, one for each part. And if it detects the magic feature of that part, it will say this is a dog leg or a cat head or whatever it's being trained on. So it's got a lot of interpretability for that purpose. Okay, so we do that. That method is state of the art on this data set. Admittedly, not hard because not many people have worked on this data set, but still it's state of the art. Okay, that gets it accepted into this conference. What I'm accepted about is that understanding of what it does tells you more. It says once you've learned this magic features, then the network is going to be robust to occlusions. Because I give you an image of a dog's leg, I occlude some part of it. Okay, I compute the features on the non-occluded subregions of the part, they're going to be these nice magic features. It's going to tell me it's a dog's leg. The features computed on the occluded bit, they're going to tell me something else, but it doesn't matter because the bits on the non-occluded part, these nice magic features, they have said this is dog leg. So I'm getting dog's leg, even if some of them is occluded. Okay, that's the core idea. It's really quite simple. None of the reviewers commented on that at all, which disappointed me. But I liked it because I said by taking this basic transformer, taking the insight that we had that Qi Hang and our collaborators at Google, I should say Jay Cheng and others had, meant that we could formulate it in terms of k-means clustering of features, which meant we had nice magic interpretable features, which then meant the whole thing would be robust to occluders without even needing to be told what an occluder is and never having been trained on one. So that's something I really like, and I'm sad that the reviewers didn't like it or didn't notice it, but I'm happy that the paper got accepted anyway. There's also potential that if you understand that, you take other types of transformers because they have very nice architectures and you can modify that, you can get other algorithms, you can get things which can be robust to those by that method or by a different method. But that's, I think, a property of having a model that you can interpret, you can know what the internal bits are doing or have a reasonable conceptual picture of it, and you can see that it's going to work well for that. Okay, here's more details. I think I'll skip over these for reasons of time. Okay, here are numbers, lots of tables that everybody loves, at least reviewers love. Qualitative comparisons, I prefer more. Experiments, robustness against occlusion. Okay, here you can either try and find occlusion in benchmark data sets, which takes time. We've done that. You can just put in the occlusions, Photoshop them in. Some reviewers don't like that, but we say in our other papers, the results when you photoshopped in the occluders are the same as when the occluders occur naturally and you've annotated them. And you get nice robustness in these cases. So, okay, so the conclusion is, right, this is a type of deep network algorithm. It's got nice properties. It is able to be robust to occluders because of its underlying structure, and it can, far more robust than any standard transformer thing applied to that problem. Okay, so that's robustness to occluders. Time going? Yeah. 10 minutes.
No, you probably just you probably have to
Wound up the talk. Okay, that's good. So here is the second set of 2D comp nets, which can be robust to occlusion. I thought this was 45 minutes. 30. Okay, sorry, misdone it. Okay, so here we have a type of generative networks which can also be highly robust to occlusion and even occlusion picked up in very different ways. These are not perfect by any means. They perform, this works for a limited class of objects, but you can have algorithms which cause deep networks to have failure modes of 99%. And these algorithms will be more robust by orders of magnitude. And again, the point is that we don't just blindly take a transformer or other types of deep network. We take it, we construct it in a generative way, and it works a lot better. It's a lot more robust. Okay. Okay, I shouldn't have spent so much time preparing these things. Sorry, well, for that. Okay, here's another class of models. Again, 3D models which are trained on 3D data. These are far more robust. Let me see if I can find an example. Okay, we can detect and classify a car here and estimate its 3D pose at the same time, despite this gigantic cat that happened to stroll into the image. So these algorithms for these classes of objects, they will perform as well as standard deep nets on classification. If there's no occlusion, they will perform enormously better when there is occlusion. They will estimate the 3D pose of these objects as well as anything when there is no occlusion. They will estimate the 3D pose even better when there is occlusion, etc. So I think challenges to robustness and challenging to the fact that the space of images is enormous is an interesting challenge. But I think here the examples so far are cases where we have done where to do it. We've needed to modify the algorithms in very different ways so they're interpretable, etc. And it's understandable why they could have these robustness properties instead of just throwing in more data and learning for a lot. Adversarial examiners to wrap up, and here is to guarantee the algorithms are robust. We need to search over the set of stimuli for worst cases. How to do it? We can't show every possible stimuli. We haven't got time. If we do random sampling, that's not good. We've had a couple of papers on this in the past. This is the type of attack that I said is 99% successful against standard deep nets, but the 2D comp nets that I didn't have time to tell you, they are an order, sometimes 2 orders of magnitude more robust because they have within them knowledge of what an occluder is and how to deal with it. Face recognition, this was CVPR last year. You can use these methods to test face recognition algorithms and find that they make mistakes, which everybody knows. Anyone who reads the newspapers knows that face recognition algorithms make mistakes. Where you take these algorithms, the same ones, you test them with random sampling, and they seem perfect. Their performance is really good with random sampling, standard evaluation, adversarial robustness. This is in collaboration with Nathaniel Brewers at Boston U and actually with Ji Hang at UCSD. And you can find problems with these algorithms that you would not find otherwise. The particular version that's going to be here this year from Ki Hao Liu is testing of adversarial of human pose. So, okay, there are algorithms for estimating human pose. There are some very good ones, particularly from Michael Black's group, pair algorithm, etc. Now here you can simulate data, you can simulate all possible poses, instead of testing again by randomly just sampling, you test, you train reinforcement learning systems that can modify the poses using feedback from the algorithms to find the ones that are bad. Okay, they don't need to know the interior of a deep network. They only need to know the output. They need to know whether it's, its sort of level of certainty. And then you can start finding where these, where the failure modes are. They're not very bad because actually some of these algorithms, the 3D pose estimation, are really good, but they do exist. Certain poses, configurations are not good, and the adversarial examiner can find them. Once you found them, in this case, I have to admit that the existing pose algorithms like pair are good, so that if you train them with their failure cases, they do better. But still, if you don't test them adversarially in this matter, you find, you think they're good, you find weaknesses for particular poses, etc. There'll be a method for testing everything, all computer vision algorithms. Find out where the weak points are. Can they be fixed by training on the weak points, which happens in this case, or to fix them, do you have to modify the algorithms, as I was suggesting and would have discussed more, the k-means transformers, the 2D comp nets, the 3D comp nets. So here is the summary, I guess, 1 minute or 2 minutes. Well, actually, of this, and then there's a summary of part 4. Adversarial examiners are a far tougher way to test algorithms. I'd like to say that high-tech companies are using them. I'm not sure that may be proprietary knowledge, but they are doing similar sorts of things. You test these things seriously, you test them, you really test them hard, because otherwise, unless you're crazy, you're not going to produce a system that's going to work in the real world. I mean, okay, I drive a Tesla sometimes. I would never use the automatic algorithm of the Tesla to drive my car for obvious reasons. I would trust a company that tests algorithms in this way far more than I would trust Tesla. So I think these sorts of testing, this is sort of extending the idea of robustness, which for me was originally, you take the images, you do tiny little perturbations to find there are problems. I'm saying you need to think of it as doing far bigger perturbations, adding objects, changing the weather conditions, or more extremely, having essentially a 3-dimensional model of the world, in this case, 3D pose, being able to generate or simulate all sorts of viewpoints, configurations, having a strategy to search over these configurations. We chose reinforcement learning, other ones could be done, and having a strategy to do that and find out where these algorithms fail. And so this is taking robustness to extremes, but I mean, we want algorithms to work in the real world. We want to build algorithms with the capability of doing it. We shouldn't have to prove it. The companies can prove it by, with all their data sets and stuff like that, but we academics ought to at least be realizing that there was a problem here and we ought to be addressing it and not wasting our time just getting slightly better results on bigger data sets where the training data is similar to the testing data, because that's been done over the last 10 years. It's been successful, but enough of that, we ought to move on. So robustness is really important. We need to make robustness even more important set of the currency algorithms. Will the current deep nets be able to deal with this? I don't think so without changes. Transformers, I gave you an example where a certain change of the transformer was able to deal with occlusions. The compositional things which I didn't talk about, they had models of object structure which were better. They could deal with things too. There are examples. I wish there were more, and from my group, I wish there were more examples like that from other people, but if there are, I haven't really seen any of them. So I think in that case, changes of the networks makes the AI more robust and more able to deal with these types of challenges. And so this is obviously, I'm passionate about this. I think unless we test our AI algorithms properly in this serious way, we're not going to produce good AI algorithms. Weak testing gives us weak algorithms. Fine, we ought to move on to tougher algorithms and tougher tests, which the companies want to do anyway, or anyone who wants these things to work in the real world, unless they're crazy, again, to retire. Okay, we ought to be doing it as academics, not waiting for the companies to do it. And then we ought to be seeing whether algorithms we have already can work, or whether we have to make the sort of changes that I didn't have time to tell you about. Okay, so thanks. I will stop now. Thank you. Questions? I think you were slightly ahead of him. Yes.
Yeah, sure. My name is Choi. I'm fifth year PhD for university. So I have a general question, like the disconnection between academia and the industry robustness. So basically, in academia, in my opinion, they're pretty good at defining scenario, like a small noise or the patch or the occlusion, and they are the adversarial domain. But in industrial, they more care about like the distributed generalization or performance. It's really hard to persuade them to do the robustness, like some adversarial guide who are not existent by so far, and they still have not a good performance against the system. So when we enter, at least when I'm doing my intern, but trying to persuade them to the robustness, they're not very interested in. They're more like interested in the output distribution generalization. But those generalization is really hard to categorize. Let's see, we cannot see. Okay, we come up with certain like noise that can represent that scenario. And if you are only doing adversarial training over a certain category, it's really hard to improve over those cases. It's really difficult because the distribution is essentially very different. Like even if you have 100% robustness against one noise, it's hardly improve anything.
Yeah, it doesn't matter. I mean, you've got to model the real world and the things that happen in the real world. And I think, the original idea of taking the images and perturbing them, that was really good. We learned a lot from it, but then people kept on working on it for years. I mean, it was like, that was something we should have done for a bit, but then it's like the MIT code you turn into, spherical cow disease. Spherical, you get top rank applied mathematician to analyze cows to see problems, and he spends a year, takes lots of money, and says, okay, well, first, let's consider a spherical cow. Fine, nice mathematical formulation, but doesn't help the farmers at all. You've got to deal with the situations that happen in the real world. We need to have data sets on that, benchmark data sets. My group is focused on inclusion because this happens everywhere, except sometimes, not much in data sets, but it happens in real life. You can paste that in, that's one thing. We've done other cases out of distribution, you change weather conditions, you change viewpoint, you do that. There needs to be a lot of those types of models. And then we may be working on something the companies would like. So if I talk again to my friend, okay, would you support me to do this sort of research? He says, no, we've got practical problems to solve, and okay, this research ought to be done anyway by academics. And it's up to us, and then when we've got solutions to them, then they will care, and then they will give us jobs and things like that. So I think we academics, we define a problem, we get stuck in it, and I think that's happened to robustness to small perturbations. And I shocked one of our faculty members who had some nice theoretical results about that by saying, I don't care. It's okay, that's a spherical cow. It's nice to know about spherical cows. It's the first thing to do, but you don't stop at spherical cows. You can put on some more realistic cows. So adversarial small perturbations, it's good to start with that, but academia, once the problem has been defined, it just has a life of its own. It keeps going for 20, 30, 40 years. Take me sometimes when it shouldn't, we should move on. Right. So that's my concern. We need to have tougher tests which are more related to the ones that have happened in the real world that the industry tests are. Does that answer your question, more or less? Yes. Gives me an excuse for another rant about subject. Okay, sorry, you had a question.
So my biggest connection so I had a question regarding like overall bit of adversarial training. So typically when there is a like kind of adversarial example, it's like train or include those other training data and then test from that, and it was good. But I just my concern is like, is there fundamentally wrong with evolution of networks or like this kind of neural networks where like whenever there's a new type of adversarial example, it doesn't work with those. So what do you think?
Yeah, I mean, I think if it doesn't work on the data, then the next thing is to modify it, give it that extra data to work on, etc. Now there were technical things, back to normalization, and heavily involved in understanding that. That's important. That enables it to work. But I think that approach of you get training on the extra stuff doesn't start breaking down. I didn't have time to talk about the 2D complex stuff, but there we did take algorithms, train on data, we test on inclusion data, and we start giving the deep networks the included data and allow them to test on it. And yeah, they get better, they get quite a lot better, but they don't do very well at the end. If you take the 2D complex, which is a different type of architecture that had within them some idea that parts of the image could be included and may not correspond to the object model, they did way better. Now, they're harder to do for technical reasons, but I think making those sorts of modifications is really important, and I think otherwise, if the deep network uninterpretable system breaks down, what do you do with it? You just give it more data and hope. I mean, yeah, I think if we had to interpret the models, understand what's going on inside them, that gives us an idea of where they can break down, where we need to improve them. And again, this is what technology does. If an aircraft breaks down, which fortunately happens very occasionally, usually I'm told it's a combination of about at least 3 different faults that happen by coincidence because they have fallback systems. But the point is that the aircraft designers know what those faults are, what can happen. And so if an airplane breaks down, they can analyze different components and see which bits need to be fixed. So I think we need that. And that means we need algorithms that are interpretable and not just black box and not just throwing data at them. I think having a taxonomy of the different types of robustness that we want to have in the real world, which relates to the earlier question, would help. And for ourselves, occlusions seem to be an obvious one. Weather conditions seem to be another one. We made a data set about that with different types of benchmarks. But more and more of those, there should be a lot of work exploring that, I think, from this perspective. Yeah. Question.
So I very much agree with you that testing against adversarial noise is. I agree entirely with what you said, but just to get your idea on a couple of possible objections regarding the program you identified. Can we really rely on testing even if aided by RL? Because ultimately testing will only be looking for a finite number of possibilities. Don't we need something that explores the continuum for other methods, for example, verification, or for example, other methods? That's point number 1. Point number 2, regarding specifications, precisely because of what you said, what reality can throw at us, there's so many possible perturbations. And sure, everybody will agree that occlusion is super important, both is super important, lighting conditioning is very important, and so on. But how can we conquer all the, if not all, how can we conquer a broader space of everything that we could be expressed?
Well, it may not be easy, but I think we need to do it. Also, I'm strongly influenced by human, models of human perception, and humans seem to manage to do these things pretty well. So it's possible. Though I think the models that humans have are really pretty different, and how they are learned is very different. They're learned during development, they're learning with multimodal cues and things of that sort. You don't just take objects, you pick them up, you play them, you drop them, and everything like that. So, those have knowledge about the 3D world, and the human ideas of human cognitive science studies, and people like Joshua Tenenbaum at MIT are wonderful at expressing them as saying human infants are building models of 3D world, and AI should be doing the same thing. And yes, it's difficult, I think, as he said in the keynote speech, lost CVPR, but that's what we ought to be doing. And so, yeah, I don't know, we can't maybe taxonomize them yet, but we can taxonomize the more important ones and go further and further. And they're important, and that, you know, they can be important also just in terms of it matters, you know, car companies, you know, you don't have much data about babies on the road ahead of your car, but obviously you care about that. So there are certain configurations that matter. I think I've only answered part of your question. What was the missing part?
As a sequence of you know, however, you know, well guided URL versus analyzing the continuum.
Yeah. Well, the adversarial examiners were essentially, and you know, doing a part of the continuum, using the reinforcement learning strategy. Is that adequate? You know, that's going to run into problems sooner or later. You know, DeepMind is wonderful at making reinforcement learning do things you think it never could. But I agree, there's going to be limits of doing that. It seems that you do have to have some notion of breaking the problem down into different parts, compositionality. For example, if you've got humans interacting with cars like opening doors, well, you could try to do adversarial examiners on the humans first, because we know how to do that, and well, their fingers in the right place, adversarial examiners on the cars, and then something about putting them together. So I think we may have to have some degree of modularity formulation of these problems so that we can examine individual modules of them. Otherwise, a huge big system, we haven't got any idea. But I think the huge big systems where we don't understand, that don't have any modularity within them, except possibly implicitly, they're going to be great for publishing papers and making our H numbers enormous, but I don't think they're really going to be solving the problem. So we have to get some of these old AI concepts, modularity and stuff like that, peek into these systems. And I think also the idea of there being a world out there, we're doing a consummation of the world. It won't be perfect initially. It may not have to be. Blind people can get around in the world without having a really good model of it. They're able to function, but to think in that sort of way and move into that direction, I think, if you agree with that. Yeah. Okay. Okay, thank you. Thank you for that.
So the next thing for the oral session, different targets here for you had to
There, so now there. Huge problems here.
Yeah. That should be allowed. So you can direct the first things here. And the also.
So. Yeah. Yeah. Okay. That's done.
Okay. All right. Hi, everyone. I'm Charles Godfrey. I'm very excited to share a little bit about our paper, how many dimensions are required to find an adversarial example. All of this is going with Henry Kavinke, Elise Bischoff, Miles McKay, Davis Brown, Tim Doster, and Eleanor Byler. So our motivation comes from this sort of recent trend of adversarial examples in subspaces. So a number of recent works consider the case where an adversary can perturb either a limited number of parameters governing the model input, or perhaps a subset of modalities in a multimodal problem. And in both cases, adversarial examples are effectively constrained to a subspace, say B, of the ambient input space X. And we investigate how adversarial vulnerability depends on dim B. Our main finding is a functional form for adversarial success. Here we're considering standard PGD attacks with LP norm constraints. So in the words of the previous talk, perhaps a spiritual cow, but it allows us to do this analysis. And we find that adversarial success behaves like a monotonically increasing function of epsilon times dim B over dim X to the 1 over Q. So here epsilon is the perturbation budget, and 1 over P plus 1 over Q equals 1. This functional form is easily derived from a toy linear model, which lends further credence to arguments that LP adversarial examples are just endemic to locally linear models on high-dimensional spaces. Turning to our experiments, we look at PGD attacks in random subspaces. So we fix an image classifier F trained on a data set E, and then for each sample XY in the data set, we generate a random subspace B by uniformly sampling dim B standard basis vectors. And then we run PGD to find adversarial perturbation of the form X prime equals X plus delta, with the property that delta is constrained to the subspace B, and the LP distance from X prime to X is at most epsilon. And then we just record whether the attack was successful, namely this indicator function of the model output not being the correct label, and finally average over the data set D, and we'll call this adversarial success. Here are some results for L infinity PGD adversarial attacks on an ImageNet ResNet 50. And on the left plot, the x-axis is the perturbation budget epsilon, y-axis is adversarial success, and then the different curves represent different dimensions of B, actually the fraction dim B over dim X. And what we see is that when we reparameterize the x-axis to instead measure epsilon times dim B over dim X, all of those adversarial success curves just fall right on top of each other. And this is what we mean by adversarial success being a monotonically increasing function of epsilon dim B over dim X. And then we have analogous results for L2 norm constraints. Here, when we reparameterize the x-axis as epsilon square root dim B over dim X, which is coming from Q being 2 instead of 1, we again find that all of the adversarial success curves fall on top of each other. Finally, we have some mathematical analysis to go with the experimental results, where we're looking at constrained FPSM attacks on linear models. So I said it was going to be a toy model. Here, we let the input space X be Rn, and we suppose f of X is just this linear function W transpose X plus B. And we let B be a subspace of dimension B, and we assume that there's an isometry U from RD to V with respect to the LP metric. And then in this toy model, we can compute the LP margin of X in closed form as the absolute value of f of X over the Q norm of W transpose U. And using that, we can show that the probability of X admitting an adversarial example in V with LP budget epsilon is just the probability that the absolute value of F is at most epsilon times this Q norm of WT. And lastly, we show that in expectation, this expression Q norm of W transpose U is D over N to the 1 over Q just times the Q norm of W itself. And this is how we show that approximately the probability of X admitting an adversarial example is a function of epsilon G over N to the 1 over Q. Happy to chat more about experiments on this analysis at our poster. Thank you all very much. Thank you.
Thanks for watching this video. Today, I want to introduce our work, CVPR workshop.
The same sort of string. Okay. Okay. The missing.
Watermark protection. The watermark vaccine is a protective defense mechanism that targets blind watermark removal networks used by adversaries to remove watermarks from digital images. Our work is an extension of this system, specifically enhancing universal. Universal adversarial contributions are a type of adversarial contribution that can be applied to multiple different images without the need to generate a new contribution each image.
对，本来我不打算管我在哪里，就是他们3、4个班嘛，我就过来。本来这一个都没来。
In this paper, we propose a universal watermark agnostic constraint against blind watermark removal network, but universal watermark vaccine, which can see that different images after being directed to the same applications as new pathogen or a new pathogen. So watermarks of watermark removed images are not completely removed. The watermark vaccine generation can be formalized as an optimization problem with constraints. In this section, we follow the work of the watermark vaccine and refer to their formulation. Unlike them, our specific challenge lies in devising a method to achieve propagation universally across all images, building upon the foundation established by their work. One way is to identify a universal propagation that acts on the entire image, thus creating a new type of view that can be added to any watermark image. This method has been previously employed in the universal adversarial perturbations for classification networks. Another way is to create a perturbation that specifically targets the watermark by utilizing watermark positional information. This perturbation, known as MUWD, offers the significant advantage of minimizing the impact of image quality. Which side minimize the loops to generate the vacuum that can make the output of the watermark removal network relatively easy. It will express the removal network recognized and the output still represent the watermark, and they tend to be the same as watermark image increase. In our experience, we show the effectiveness and university of our methods. In each row, we show the watermark removal effect in the images without any vaccine, the images with UWP, images with MUWP under the same antivirus. We also compare UWP and MUWP under different projects by displaying images each row. We can see that MUWP exceeds FDM results either with a lower requirement or UWP required a higher requirement. However, those methods perform well and met our expectations. In conclusion, we developed an idea from the universal watermark vaccine to protect watermark technologies based attacks by malicious attackers aiming to remove or alter the watermark. Which is difficult to protect from the to overcome this, we propose videos for using university to safeguard the watermark from elimination by existing removal networks. Ensuring contain integrity and quality. However, we don't need to protect the removal points. The weak license can move and to present our view. Where you is strongly resistant against the non-management. Our way is for university for moderated and really further exploration in future.
Right. 出去麻烦，特别麻烦。
Ladies and gentlemen, good afternoon. I am Wang Haoyu, a student from Huazhong University of Science and Technology. I am currently interning at Real AI. It is an honor to be here at the CVPR 2023 Art of Robustness workshop to share my insights on competition techniques. I look forward to presenting my research findings and contributing to the discussions on enhancing robustness in computer vision. Thank you. The competition focuses on vehicle detection in the physical world and aims to build robust models against noises. Phase 1 includes the train and test set shown on the left image, while Phase 2 includes the train and test set shown on the right image. In both phases, the train sets contain only normal samples, while the test sets encompass adversarial camouflage, adversarial patches, and other challenging scenarios. Next are key points and challenges: adversarial camouflage generation, pseudo-label usage, weighting loss functions, non-visible test set. To address these challenges, participants should focus on data optimization by constructing diverse adversarial examples, and employ model optimization techniques like EMA and SAM to enhance robustness. The method framework consists of a model training process and an inference process, and specific techniques within this framework will be discussed in detail later. One core aspect of our method is data augmentation, which includes local augmentation such as generating adversarial examples based on FCA and dual attention attack. In addition, online augmentation is employed using pixel level and spatial level transformations. Through data augmentation, our model gains improved generalization and enhanced robustness. In our approach, considering the limitations of parameter size and flops in the official model submission, we have opted for the YALOV 5L network structure. As we have not made any modifications to the model structure, we will not delve into its details. For further information on the YALOV 5 model, I recommend referring to the official YALOV 5 website. In our training strategy, we have introduced SAM, sharpness-aware minimization, a technique that aims to enhance model generalization by minimizing a sharpness metric of the loss function. By optimizing for sharpness, SAM promotes the generation of stable and flat models, resulting in improved robustness against weight perturbations. Similarly, in our approach, we also utilize EMA, exponential moving average. EMA is a technique employed during training to create a smoother and more robust model. During inference, our method utilizes multi-scale inference and post-processing with threshold adjustment to improve the accuracy and reliability of object detection results. The combination of multi-scale inference captures objects of different sizes, while threshold adjustment fine-tunes the confidence threshold for a better precision recall trade-off, enhancing overall performance. These two figures illustrate our team's scores during both Phase I and Phase II of the competition. Next, we present the results of our oblation study on the methods used during the competition. In conclusion, we have shared our approach and key insights from the competition. Our focus was on enhancing robustness and accuracy in vehicle detection. We appreciate the opportunity to participate and are eager to refine our methods further. Thank you for your attention.
Hello, everyone. I am honored to share our winning project with you today. I would like to talk about our project and share our experience. First of all, let me introduce the content of the competition and analyze the corresponding difficulties. The focus of this track is to develop robust object detection algorithms that can eliminate the influence of the natural interference, adversarial camouflage, and other disturbances. To solve the above-mentioned challenges, we designed the following algorithm framework, which mainly includes the following key points. First, we primarily simulate natural interference to augment the training data. Second, we employ strategies such as multi-scale input augmentation. Last, we design a parameterized dual tower perception model. In the competition, we also found some effective ways to increase points, and here we share them roughly. First, we incorporate test time augmentation techniques during both training and testing stages. We implement an image corruptions data augmentation strategy. Second, we introduce a partial cutout operation for detection objects. Last, we employ adversarial YOLO algorithm for adversarial attacks. Besides, we introduce Gaussian noise maps and select 100 data samples with camouflage textures in the initial phase. At the end, we conducted the ablation study, and as you can observe, each of the models we mentioned were effective. We implement the VTTA inference strategy, which includes non-augmentation strategies to further improve the robustness of the model. By combining with the parameter twin towers and WBFNMS, VTTA achieves a final online score of 70.4, securing the second position on the leaderboard. We would like to thank all of the judges, organizers, and my fellow competitors for making this such a memorable experience. Thank you for listening.
Hello everyone, I'm very glad to have this opportunity to share with you our solution for this vehicle detection defense competition. I am Zhao Yikai, the keynote speaker, with a master's degree from University of Science and Technology, Beijing. The sharing will focus on the following aspects: competition analysis, approach, ablation study and reference. First of all, I introduce the competition in brief. The competition is divided into two phases. The phase one for vehicle detection, training data 600 and test data 2000. The phase two is the PVB detection with 200 training data and 2000 test sets. It can be seen that the amount of data in the training set is very small. So how to obtain more training data is the key factor of this competition. In the phase one, we collected 15,000 and 500 clean color simulation data of DAS paper, and one also sample was provided by DAS and FCA paper respectively. We pasted the two adversarial samples on the clean data respectively. The training sample picture with DS and FCA adversarial sample respectively is shown on the right. In the phase two, we randomly selected 6,000 images from the training data of the phase one for vehicle. For pedestrian and bicycles, we collected 5 adversarial patches from ADV YOLO and TSUV paper and pasted them onto 200 training samples respectively. On the right is a picture of a training sample for pedestrians and bicycle case with an adversarial sample. Table 1 shows the results of different detection models in phase 1. Table 2 shows the comparison of the effects of different YOLO detection models in the phase 2. Table 3 shows the effect of different amounts of training data, different iterations, and different enhancement tests. The conclusion is that the number of iterations should not be too much, which is easy to overfit. The enhanced test adopts the multi-scale test and the left-right flip, and the effect is very obvious. This is a list of reference for this competition. Thank you.
Okay, let's go for the morning session. For people join over Zoom, we will start like 1 hour later. See you guys there. Yeah. So we will start the afternoon session like 5 minutes later. So yeah, that's set up here.
morning, good afternoon, and good evening. I'm Ling Zhen, the head of privacy and security team from Sony AI. Today, I'm happy to be here to give an invited talk titled Towards Robust Priority Learning. So as you may know, there are a lot of different types of robustness in priority learning, such as adversarial robustness during test time, robustness to out-of-domain distribution during test time, and Byzantine robustness during training time. Today's outline will mainly focus on three components. The first of all, I would like to introduce the background of priority learning, followed by two robustness in priority learning, in particular the robustness in test phase and Byzantine robustness in training phase. Here is a typical priority learning process. As you may know, priority learning provides a privacy-aware learning paradigm, so which means it allows participants to keep their local data without sharing with any third-party servers. The only thing they need to do is to share their local model parameters with the central server. Then the central server will aggregate the received local model parameters to get a new updated global model. Then the participant will download the updated global model from the central server and use the global model to do the next round of the local training. So the whole process will iterate in such a manner. So as you may see, the distributed property of priority learning will open new spaces for the attacks. For example, both the central server and any participant could be the potential adversaries who can launch adversary attacks and malicious behaviors in order to corrupt, to compromise the integrity of the priority learning system. One example is adversarial robustness during the test phase. As you may know, in centralized training, actually the trained local models would be vulnerable to adversary attacks. Here is a very famous example. For example, the original image is a panda. By adding a small perturbation, actually the machine learning model will misrecognize it as a gibbon with a very high confidence. And actually the similar story also applies to priority learning. Priority learning is actually also vulnerable to the well-crafted adversary samples during test time. And attackers can add also a very small amount of the perturbation to the test data to mislead the globally trained model to predict wrongly to the adversary examples. A naive solution is called federated adversary training. So which means instead of doing standard training on local participant, or the local client, they will conduct instead the robust adversary training. However, there are some problems in the conventional federated adversary training. As you may know, always adversary training is more difficult and challenging than the standard training. And actually, this problem becomes more serious, more challenging if the data is non-ID in priority learning settings. And as you know, adversary training usually requires more data and also takes relatively more computation resources compared with the standard training. And as you can see from the right figure, actually this conventional priority adversary training will deliver much slower convergence and lower natural accuracy compared with the standard priority learning. To solve this problem, so we proposed a new approach called GALE, a margin-based priority adversary training approach. So in this approach, we encourage the minority classes to have larger margins, and we regularize the decision boundary to be smooth. In more concrete, in the loss function, there are two components. The first component is called margin-based cross-entropy loss, in which we aim to make the minority classes to have larger margins. And the second component is called regularization loss, in order to make the decision boundary to be smooth. By using our proposed approach, so we can make sure that the federated adversary training can achieve better performance and convergence. And this work was recognized with the Best Paper Award at FL AAA 2022. However, this work lacks of any theoretical guarantees without any analysis to explain why it works and also discover the root reasons behind the failure of the conventional FAT methods. So we extend the previous work to New Ip's 2022 paper called CAR-FAT, the calibrated federated adversarial training. So in this work, we firstly find out the root cause of the low performance and the bad decision boundaries of the previous federated adversarial training. The main reason is because of the screwed label distribution in federated learning setting. In more concrete, so here is an official definition for the screwed label distribution. So for any two participants in federated learning, I and U, so their label distributions could be different. However, given a class Y, their input could be sampled with equal probability at different clients. So actually, this assumption is valid in real scenarios. So for example, given a class of cat, actually all the clients can have an equal opportunity to sample all types of cats. And we also find out that the standard cross entropy loss will lead to the heterogeneity problems. So this is because in previous federated adversarial training methodologies, so each client will estimate the local class probabilities by using this formula during their local training. However, since their local data distributions are different across different clients, their local class probabilities will be non-ID. And actually, this non-ID problem will lead to the heterogeneity of local models. As you may know, by aggregating the heterogeneous local models will result in the convergence problems, even result in the divergence of the global model. To solve this problem, so we proposed our calibrated federated adversarial training with the aim to learn homogeneous local models by calibration. In particular, we calibrate the class probabilities by introducing a class-wise prior. So the detailed deduction can be referred to our paper. So here is the experimental results. We conducted our experiments on 4 datasets, including the Cyberton, Cyber100, SVHN, and ImageNet subset. We tested the natural accuracy and robust accuracy against the most representative adversarial attacks, including FGSM, BIM, CW, PGD20, and AA attack. As you can see, our proposed CAR-FAT outperforms all the previous federated adversarial training methodologies. And as can be evidenced from the right figure, both the natural accuracy and the convergence code becomes better compared with the previous federated adversarial training baselines, including the FAT-PGD, FAT-Trace, FAT-MART, and so on. Some takeaways for this work. So we firstly find that the previous federated adversarial training methodologies may result in the homogeneous local models. And these homogeneous local models tend to give the higher scores to the majority classes, while lower scores for the minority classes. To address this problem, so we proposed new approaches in order to encourage the local models to give higher scores to the minority classes by adding a class-wise prior to the logics in order to lead to the homogeneous local models and result in better convergence and performance. Next, I will dive into the Byzantine robustness, which is a training phase robustness concept in federated learning. As you may know, So because of the distributed property of variety learning, so any malicious participant can launch both the data poisoning and the model poisoning attack in order to poison the globally learned and compromise the integrity of the whole system. And actually, according to the objective of the poisoning attacks, those kind of the training phase robustness attacks can be categorized into two components. One is the untargeted attack, such as the Byzantine attacks. So in which the Byzantine attackers can send any information to the cloud server, and the honest client will follow the protocol and send the honest gradient or model parameters to the server. And another type is called the targeted poisoning attack, such as the backdoor attack or the symbol attack. So in this talk, I will mainly focusing on the first untargeted Byzantine attack. So here is an illustration of how the Byzantine client compromise the whole variety learning system by sending the Byzantine gradient and upload to the server. In terms of the assumptions, so we just follow all the previous works in terms of the goals for the Byzantine attacks. So basically, the Byzantine clients will conduct untargeted attack, and with the aim to reduce the overall performance of the main task of the priority learning system. Moreover, going beyond, so we also made some very practical assumptions here. For example, we assume the Byzantine clients, they can have access to the honest gradients of all the honest clients before conducting the attack. And the Byzantine clients can even know the defense strategies launched by the server, and also the Byzantine clients, they may collaborate with each other. In terms of the robust aggregation rules to defend against the Byzantine attacks, so actually we categorize the most existing Byzantine defenses into two types. The first type of the robust aggregation rules try to aggregate all the honest gradients, such as the multi-crom, RFA, and DNC. Another type of the robust aggregation rule will aggregate fewer gradients, such as the medium, RBTM, and Boolean. We also discovered some challenges in the existing Byzantine robustness mechanisms. The first challenge is that the robust aggregation rules that try to aggregate all the honest gradients may suffer from the curse of dimensionality problems. So which means the Byzantine gradient can take advantage of the high dimensional property of the gradients and easily circumvent the robust aggregation rules. So here is an illustration of how the Byzantine attackers can circumvent two representative AGRs, including the multi-crom and the RFA. Another challenge is that the robust aggregation rules that aggregate fewer gradients cannot handle the gradient heterogeneity problems, especially in the non-ideal settings of variety learning. So which means the global gradient will deviate from the optimal gradient and result in low performance. For example, the media and RBTM falls under the umbrella of this type of the robust AGRs and suffer from this kind of the problems. And to the best of our knowledge, so no existing robust aggregation rules can handle both the curse of dimensionality and gradient heterogeneity problems. This motivates our work published by ICML 2023, called the Byzantine Robust Learning on Heterogeneous Data via Gradient Splitting, short for GAS. So in our proposed GAS, so first of all, after the server received the uploaded gradients, so the server will split each gradient into P equal-sized and low-dimensional subvectors. So in this way, so the server can tackle the cursor of dimensionality problems. And in the second step, instead of aggregating the subvectors, so actually the server will take the aggregated subvectors as a reference and compute the identification scores for each subvector associated with each client I. And after summing up all the associated subvectors with the client I, so the server can get the identification scores for each client I. And after filtering F clients, then the server will average N minus F gradients with the lowest identification scores and output the aggregated global parameters. In this way, so the server can handle the heterogeneity, gradient heterogeneity problems. So here is just an overview of our proposed guess. And note that this proposed approach can be compatible with any other robust aggregation rules. So here is our experimental settings. Still, we mainly validate the effectiveness of our proposed approach on CV dataset, including CVPR 10 and 100 ImageNet subset and FE MNIST. We tested the performance of our proposed methodology and the baselines under the 90 settings. In terms of the baselines, so we compared with the most representative and the SOTA Byzantine defenses, including the multi-chrome, DFA, DNC, media, RBTM, and Boolean. We evaluate the performance under 6 representative Byzantine attacks, such as bit flip, label flip, LIE, minimax, and so on. As you can see from these experimental results, by integrating our proposed approach into any of the current robust aggregation rules, the performance can be largely improved under all the 6 attacks for all the data sets. So here is a summary for this work. So first of all, we point out the limitations of existing robust aggregation rules, i.e. the curse of dimensionality and the gradient heterogeneity problems, especially in the 90 settings under federated learning. And in order to solve those kind of problems, so we proposed a compatible approach called GAS that can be combined with any robust aggregation rules. And our proposed methodology is relatively lightweight and effective. Going beyond adverse robustness and Byzantine robustness, so we actually also did some attempts and contributions in terms of the robustness to OOD and domain gap settings. So our previous attempts were published by iClear 2023. Although these 2 works are mainly for the centralized setting, so we didn't consider the federated learning setting. However, all these works have the possibility to be extended to federated learning settings. So if you guys are interested, feel free to check out our recent works. And yeah, thanks for listening and have a lovely day. Should you have any questions, feel free to drop me an email. Thank you, everyone.
process. We're using an off-the-shelf generator, a conditional generator based off of diffusion-based models, text diffusion. And what we're doing is we're generating the perturbed caption. So the perturbed caption said to make orange leaves. Whether or not the whole model decides to change all the leaves or to change a few of them is not something that we're exploring in this work.
Thank you. I'm kind of curious about how do you know you're not for the class? How do you know you're not treating something that's an actual positive co-occurrence? Like say with monkeys, say like these monkeys only occur with these kind of leaves. So by changing them, you're actually potentially hurting the generalizability of the model. How like I guess like the difference between nuisance novelty and some useful.
Yeah, absolutely. So just to clarify, this is an evaluation auditing scheme. So the proposal is not to use these images for training, but rather to illuminate what are the ways in which the models are making decisions. Some of the times those decisions could be actually helpful. So for example, in the very first example of predicting the dog sled, it wasn't really visible, but because it had this particular breed of dog and this particular configuration on snow, it was able to get it correct. So that's a situation where these correlations helped us. So, but you still want to be able to know that that is the information the model is using, because otherwise you don't know that. All you know is that it correctly predicted dog sled across all of your images. So in some cases they can hurt us, in some cases they can help us, but regardless, even if they're helping us, when they're missing, we might fail to predict the category of interest because we didn't leverage the features that we thought we were leveraging.
So this method would be good for like individual images, like what in this image is the bias. So can you generalize it into data sets? Like here's the top 10 things in the data set, or this, I guess this model, this data set is potentially biased.
Yeah, this is where this type of class level perturbation comes in place. You need to be able to do this across a lot of different images for a consistent type of perturbation. And then you can start to be able, you can automatically sort of the average change of performance and start to pleasing on those changes.
You have like almost notice that common theme between the models, like you consistently always get this problem wrong.
I think that's an interesting direction for exploration, but we don't have any answers to that right now. Probably out of time. Thanks, everyone.
Let's take the speaker again. All right, please allow me to introduce our next speaker. Dr. Furong Huang is an assistant professor of the Department of Computer Science at the University of Maryland. Her research focuses on machine learning, high-dimensional statistics, non-convex optimization, spectral method, reinforcement learning, and deep learning theory. The thesis of Dr. Huang's research is to understand the foundations of deep learning under distribution shifts, adversarial perturbations, and non-IID data. Through the investigation of Frank's code method that address these modern challenges in applying ML to real-world application, Dr. Huang's group expands the scope of deep learning model designed for learning in constrained edge clients and on graph data. With that, let's welcome Dr. Huang.
Thank you. Thank you for this opportunity to speak at this workshop. And today I'm going to talk about the robust reinforcement learning in an ever-changing world. So we know that we live in an era of information deluge. Even the smartest can find themselves really overwhelmed by highly dynamic and massive data streams they must keep up with to make informed decisions. So whether it's our daily life of driving at very busy traffic junctions, or healthcare and medicine that concern high priority needs, or reinforcement learning from human feedback for near human or even superhuman AGI, such as large language model updates. So reinforcement learning is essentially the canonical way to model interactive decision-making, and reinforcement learning algorithms aim to develop machine learning models for autonomous interactive decision-making. So, but what is reinforcement learning? Is there a question from the audience?
No question yet.
Okay, what is reinforcement learning? The main idea is to learn by interacting with the environment, reinforcing good behaviors and avoiding bad behaviors, just like how a toddler would learn without providing data sets with explicit labels. They would just gradually master how to behave by interacting with the environment. Well, the consequences of the behaviors are often, however, not immediately sent as feedback, but rather sent in a delayed manner. Well, now I wanted to show you a chat of like top keywords in last year's NeurIP submissions, and indeed reinforcement learning is a top 1 topic due to its wide application to real-world scenarios. Well, in the past few years, reinforcement learning does achieve a lot of success. For example, the game of Go, video games, local motion tasks, and etc. But most of these success stories are still in simulators. Now the question is, can they be applied to real-world applications such as auto driving, healthcare, home robots, market making, and so on? So are intelligent agents ready for real-world problems? Well, when agents interact with the real environment, from the environment perspective, the environment can be ever-changing. The interaction can also be very noisy and exposed to adversaries. And the neural network agents are often shown to be fragile to perturbations of input. For example, a well-trained autonomous driving agent can recognize a stop sign as a sports ball under, oftentimes small but sophisticated perturbations or changes. So when dealing with the real environment, being able to deal with unexpected changes is the key. And then we ask the question, can RL agents quickly master how to deal with the change, even when the change is adversarial and stealthy? Well, so based on the philosophy of know your enemy and yourself, here is an overview of my group's recent progress on robust reinforcement learning. We consider adversarial, robustness of reinforcement learning, meaning that the perturbation happened in an adversarial manner. So we're considering the worst case scenario. And our work covers a wide variety of cases based on when and how the perturbation happened. One important line of work we did is to consider perturbing the interactions with the environment. So we'll consider also both during the training time and during the test time. Oh, another very important line of work we did is to consider vulnerability when interacting with other agents. Well, as you can see here in the red text, I'm listing our selected publications for each of these cases. And in this talk, I'll be covering the test time robustness and multi-agent extensions. So let's start with the single agent scenario and consider the perturbations when interacting with the environment during the test time. First, I would like to show you some background on adversarial robustness and deep learning in general. As we all know, despite the success of deep neural networks, it is well known that deep neural networks can be vulnerable to adversarial perturbations to the input. And here is a very famous example where you already have a very well-trained classifier, and if you add very tiny noise to the panda image, the resulted panda image will look the same, but a very well-trained classifier may misclassify it into a gibbon. And such adversarial attacks and defenses have been very well studied in computer vision. But in reinforcement learning, we also use deep neural networks to model the policy. So it is natural to ask the question of how vulnerable our deep neural policies are and how we can make them more robust. Are the neural networks, are the neural policies more vulnerable, the same, or less vulnerable to adversarial perturbations? Actually, in this talk, as a teaser, I will argue that image classification is just the one-step decision, which is very different from real-world sequential decision-making problems. In sequential decision-making problems, often modeled by reinforcement learning, as I illustrated earlier, a single mistake not only changes the immediate result, but also changes the future. So we need to take this very special care of reinforcement learning agents in sequential decision making, which is challenging given that the environment uncertainty is often very high and we have to consider long-term decision making. Okay, so far I motivated the problem from a high-level perspective, but let's make the problem a little bit more formal. Let's first define a reinforcement learning task. And indeed, there is an environment and an agent, and the agent can interact with the environment by sequential decision making. At every step, the agent would observe a state and would take an action, and the environment would proceed to a new state. And to see how well the agent is doing, the environment oftentimes return a numerical reward, and the process goes on and on to generate a trajectory, which is a sequence of state and actions and rewards. Well, so the environment is usually modeled by a Markov decision process with a state space, action space, state transition function, and a reward function. And the agent takes action according to a policy, which is a mapping from the state space to the action space. And the goal of reinforcement learning is to learn an optimal policy that can maximize the cumulative reward. And the cumulative reward can be measured by the value function, which can be oftentimes defined by expected total reward that the agent can get by following a policy pi. Well, a lot of the recent promising progress is achieved by deep reinforcement learning, which essentially uses a neural network to model and learn a policy. So they make reinforcement learning more scalable, but in the meantime, they may also bring some potential risks, as we will discuss later. So to avoid being attacked, we should be aware of our algorithm's vulnerability. As the old saying goes, if you know yourself and your enemy, you will never lose a battle. That's why we started with the goal of learning to robustify. We'll first seek to know or to understand, to model the enemy, to study different types of attacks in reinforcement learning to understand the worst case vulnerability of reinforcement learning. Then we robustify ourselves. We evaluate and improve the robustness through defenses. So let's focus on the attacker or the enemy. And the first step is to make the attack model more clear. Well, let's consider the agent interaction, agent and environment interaction loop. So during the inference time, the agent would execute some trained deep policy, which is the victim. And the attacker lies in between the agent and the environment, trying to perturb the state before the agent observe it. Well, this is very similar to the image input, perturbing the image input of a classifier, but now the attacker makes the perturbation at every step of interaction. Of course, here for simplicity, we can consider a very common LP constraint for the attacker, but generally it applies to any kind of attack to the image or to the state. Also, the attacker can eavesdrop on the reward signal, or it can also see the victim agent's policy. Note that the attacker does not know any of the environment dynamics. So this is a very common setting in the literature because, as I mentioned before, the interactions between the agent and environment may be noisy or exposed to attackers. So then our question here is, what is an optimal attacker? Or in other words, we wanted to find a lower bound of the cumulative reward to measure the vulnerability of the victim. Here are some, there are some existing solutions for this problem. Some researchers have extended the attack methods from supervised learning to reinforcement learning by converting every single step into a supervised learning problem. And there are a bunch of different formulations for such conversion. And they propose different optimization objectives based on these heuristics. But what we show in theory is, unfortunately, none of these objectives is optimal in the sense of finding the worst case vulnerability of these RL agents. It means that even if you find the exact solutions to these objectives, which are not optimal, the solution is not necessarily the optimal attacker, and it may even be arbitrarily worse than the optimal attacker. To see why this is the case, we can consider a grid world, a very simple example. The original policy is to go right and follow the green route and find the goal. Well, however, the heuristic attack would prevent it from going right, so that it will go up or go down, which can indeed reduce the performance, but only from a myopic perspective, only in the short term. However, you can see there exists a much stronger attack in this case, which is the red path that actually first led the agent to go right to achieve some very high reward at the beginning. But then later on, when it goes right, it can actually reach some trap and get a very low reward, essentially a catastrophic failure, which is a trap here. So as you can see here, this example shows that, these kind of strongest attacker needs to consider the future steps and also needs to know the worst case events in the environment, like the trap, which requires some sort of exploration. And therefore, it is naturally a reinforcement learning problem that requires some exploration of the environment rather than a simple extension from a one-step kind of image adversarial machine learning problem. So these are efficient, but not optimal. Here comes another solution. Actually, we call it an end-to-end reinforcement learning attack. Formally speaking, the attacker wants to learn an adversarial policy and denoted by H and map the current state as to a perturbation state, as tilde. And then, the adversarial policy, the goal is to minimize the cumulative reward of the victim agent, and the adversarial policy can be learned by an RL algorithm. Well, we kind of treat the environment and this victim agent together as a new environment. And every time step T, the attacker would observe the original state as T and output a perturbation state as tilde as the attacker's action. Well, it takes the opposite of the victim reward as the adversary reward, and then you can just train the attacker with any RL algorithm of your choice. Well, the good news is that, in this formulation, it is indeed optimal since it considers the uncertainty of the environment and the long-term reward. The optimal policy in this adversary's MDP is the optimal attacker that can minimizes the victim reward. However, if you learn the policy whose input and output are both in the original state space, and the state space in practice is usually very large and high dimensional like images. And in this case, directly learning an RL adversary is really hard and even intractable. So it is optimal, but not efficient. So to summarize, the prior methods, heuristic attacks are efficient, but not optimal, while these end-to-end RL attack is optimal, but not efficient, as you ended up learning a very large MDP. Well, so the question is, can we achieve both optimality and efficiency? Answer is yes. We propose a new attack algorithm that achieves both with a good balance. Here is how we do it. Let's dive deeper into the essence of evasion attacks. So the attack perturbs the state, and the victim then selects an action based on the perturbed state. Well, this is essentially equivalent to directly perturbing the victim's policy, and then the attacker's goal is to minimize this policy value by designing some bounded perturbation in the state space. Well, this is essentially an end-to-end reinforcement learning attacker, which directly learns, which state perturbation leads to the lowest value. However, it can be a very large RL problem, as I illustrated earlier. And in theory, actually, we show that optimal state attack actually leads to the optimal policy attacker. So, essentially, we wanted to ask the question, can we consider the optimal perturbation is a much smaller policy space, right? So rather than actually directly perturbing the state, can we do some disentanglement? Can we, decompose this very large RL problems into two problems, whereas the part that, concerns the very high dimensional state space, can be reduced, let's say, to a non-RL problem, which is essentially reduces to an image adversarial perturbation, problem, and then consider another component, which is, the action interaction with the environment without even considering the state. And this problem, because it's, interacting with the environment so that, it finds the action that minimizes the value, therefore becomes an RL problem. But this RL problem could potentially be much smaller because it doesn't really concern the very high dimensional state space and only consider the actions, which sometimes could be very small cardinality. And indeed, in our theory, what we observe is that the strongest policy attacker is much easier to identify than the strongest state perturbation on the image space. Actually, it turns out, our theoretical insight says that the optimal attack pushes the policy as far away as possible towards some direction. So you only need to look at the outermost boundary of the policy space, whereas in the state space perturbation, it is not necessarily true that the state perturbation on the outermost boundary is gonna result in the worst case attacker. So this is really nice. It basically means that you only need to find a direction of the attack in the policy space and then just push the policy to the outermost boundary. And, with these insights, we propose an algorithm called a policy adversarial actor director, PAAD. And essentially, there is a director and an actor. The director would learn a RL policy that maps a state to a policy, perturbation direction, a hat. And then there is an actor which follows the instruction from the director and corrects state perturbation under the attack constraint, such that the policy is pushed as far as possible in a given perturbation direction. So in the right-hand side in the figure, as you can see, the director and the actor collaborate in the PAAD adversaries MDP, and we have more formal formulations in the paper in case you're interested. Here is just a high-level illustration of how it works. So in theory, actually very nicely, we can show that the collaboration between the director and the actor would produce an optimal attacker, and it has a lower sample complexity bound than the end-to-end RL formulation. So here are some empirical results. We essentially consider the state-of-the-art performance on many environments against a wide variety of victim agents. For example, we consider this Atari game and the DeepQ network victim, and we're able to produce the reward to the lowest possible, using very, very small perturbations. As you are familiar with, these epsilon values are much smaller compared to those traditional epsilon values used in image classification. So it is really very concerning, basically revealing that reinforcement learning agents powered by deep neural networks are essentially very vulnerable, are extremely vulnerable, more so than deep neural networks themselves. And this is because these attackers, the strongest attackers, can utilize the vulnerability in the long run. So it's a long-term vulnerability is being exploited here, and we can achieve the lowest possible reward in a lot of these Atari games. Well, actually, here is a demo. You can see an Atari game Pong, where the victim agent is actually the right green pedal. You can see, under the normal training case, the reward is very high, 21, but the previous best attacker, it's not very good, achieves a reward of -14, but still it's trying. And you can see in our strongest attacker, essentially, the green paddle basically stopped and gets stuck on the upper right corner and get the lowest possible reward here. Again, as I said, this is really concerning. It's basically revealing that reinforcement learning agents are very vulnerable. Now, we've understood the enemy very well. It's time to know ourselves to improve the robustness of the reinforcement learning agents. So at a first attempt, it is natural to consider doing adversarial training, which is, to train the agent with a very strong attack. As we say, the old saying says, whatever doesn't kill you makes you stronger. So you can see we, in this figure here in this Hopper environment, we alternately train the victim and the attacker. And this actually works well in many environments. And here is an example with the Hopper, as I see. The y-axis, the reward, and the x-axis refer to different attacking algorithms. And the bar with different colors are existing robust training methods combined with a popular RL algorithm called PPO. So the green bar are vanilla training, which are, gets very low reward under almost all types of attacks, especially under our PAAD attack. And the blue bars are an earlier baseline, and purple bars, named the ATLT, are alternately training the agent and the end-to-end RL attacker, while the red bar, called the PAATLA, are alternately training the agent or a PAAD attacker. So you can see that the PAAD attacker, as a strong enemy, essentially makes the agent more robust than all the other baselines, not only under the PAAD attack, but also under other attacks. So stronger enemy can give birth to stronger agents. And this is another important reason of starting adversarial attacks. They can not only reveal our vulnerability, but also can be our teacher and make our agents more robust. Well, this seems all very good, but is the method efficient? Well, not really. We need to train the attacker, which essentially takes extra samples, extra time, and also has convergence issues because it's a very complex two-player game. So can we do better? Indeed, the answer is yes, and we propose a much more advanced and elegant solution. So here's what we did. We consider the robustness of agents against the strongest enemies in terms of the cumulative rewards. But instead of training an extra attacker, we focus on the agent itself, and we directly compute the worst case value of the victim agent. So the key here is, we call it worst case Bellman operator. And you can see in this formula, we show that it is a contraction whose fixed point is the worst case performance of a given policy pi under attack bounded by attack radius epsilon. And what does it do? It basically accumulates the current step rewards and the discounted next step worst case rewards. Here, this AADV set is a set of actions that pi may select under attacks that perturb the state with an epsilon ball. So that is basically saying that for a given victim policy, here, as I show, for a given victim policy pi, under some original state, it would output an action A, but now, the input state can be changed within some epsilon ball, and then we would like to compute the range of the possible action output as the AADV set. So this is what that equation is showing. And this can be really easily computed by an existing technique called interval bound propagation, or its more advanced versions. And it can give basically an upper and a lower bound of the network output when the input is changed within a certain region. So by this technique, we can very efficiently compute that AADV set. And then what we do is we're going to train a network by temporal difference learning with regard to this equation. And this is an approximation of the worst case value of this policy. So we call it the worst case critic. It's very similar to the commonly used critic function, which is the clean value of the policy. So similar to the actor critic framework, we're going to use this worst case critic to direct the updates of the policy. So we optimize the policy towards the direction where the worst case value is improved. So this becomes like a plug in and play, is a plug and play component for any existing RL algorithm. And we can just train the worst case critic and add the robust policy optimization to the original objective. Well, here are some empirical results. It's very impressive that under a wide variety of attack strengths, ranging from a weaker attack, which are heuristic on the left-hand side, to the right-hand side of the worst case attacker, which essentially is like, a certification of finding the worst case vulnerability of the agent. You can see our proposed Volcar PPO, the red line, is the most robust compared with all the baselines. So it's basically achieving the SOTA robustness. And that's not the end of the story. As you can see here in this figure, not only it achieved the best robustness, but it's also achieving the best for Pareto frontier in terms of the natural reward and the robustness trade-off. This is very impressive, but even more, you can see this Volcar PPO of ours can achieve a very efficient, defense, essentially not only robustness, but also the best trade-off, and achieving those two using the least number, of computation, or use the least clock time. So is achieving basically a SOTA efficiency with 2 times better training efficiency compared with other baselines. And here is a demo. Basically, it's showing, on the left-hand side, this is a, alternately training the PAAD attacker and the victim agent. So is an adversarial training mechanism. And you can see it's basically learning an agent that jumps with one leg, which is, we suspect is kind of overfitted to a specific attacker. Whereas on the right-hand side, you can see our method, which is directly compute the worst case value and optimized policy. It actually is very interpretable because the agent learned to lower down the body is very intuitive, and it becomes a very general defense. Now, so basically with the philosophy of know your enemy and yourself, we're able to, train a very robust agent in a very efficient manner. So now I've talked about the test time attack for a single agent scenario. I would like to move on to some, multi-agent extensions here. So here, we consider the multi-agent situation, and we all live in a world, with very limited knowledge. Each one of us can be thought of as an agent with a very limited sensory range. So with the sensory range, let's say in this example here in the great world, you only observe your local environment in the great world, and your goal is to find the gold rather than, go to the bomb. So of course, at the beginning, because of your limited sensory range, you don't know whether to go up or to go right. However, if you have other agents that are spread out in the great world that are your friends, then communication can really alleviate this problem of partial observability, because the other agent in the environment can just communicate to you what they observe. For example, these agents will tell you that, at the location 11, there is gold, and at location 44, there is a bomb. So naively, this would be helpful because, if you make decisions based on your own observation as well as the messages from the other agent, then it's very nice that, you know, you could probably just go to up because you know that on the right there is a bump. But this is very naive by, you know, just naively aggregating all the messages. However, if you have some agents, let's say, you know, due to sensor failure or due to, you know, communication noise, or even due to some enemy attack, the agent is under attack and compromised, then they send you some misinformation. You know, for example, in this case, the agent will send you that there is $1,000 at location 44, whereas the other friendly agents that there is $100 at location 11. Then of course you want to go right because $1,000 is way more than $100. But this causes a problem because this malicious message M3 would lead to the catastrophic failure of going right, you know, just because you are weighting all the messages in an equal manner so that you consider all the message and think that, you know, $1,000 is way more than $100, so you choose to go right. So indeed, communication can carry misinformation or adversarial attacks, and it can be a double-edged sword. Now, the question is, can we find robust policies that not only, you know, kind of consider the partial observability constraint and take information from other agents, but also be aware that other agents might not be trustworthy. And indeed, in this work, we propose to have this kind of robust policy training algorithm that the basic philosophy is to trust some consensus rather than an individual too much. So our proposed method works as the following. During the training time, you know, we call it a bladed message ensemble. During the training time, you observe all the messages from all the other agents. So there, let's say there's n agents in the system, so you would observe n-1 messages. Because it's training time, so you're relatively safe and your messages are not corrupted, so they're all benign. So what you choose to do is to do some kind of ablation. Rather than use the entire message to make the decision, you choose to randomly select K messages out of this n-1 messages and construct these ablated K message samples. Now with these K message samples, what you can do is you can, you know, train a base policy that, you know, try to come up with an action based on these ablated K message samples. And this is really nice because during test time, when you are under, you know, corruption, when some of the messages are indeed corrupted, you could reuse some of these base policies. So when the messages are corrupted, you're going to still, you know, construct some of these ablated K message samples, but unfortunately, some of them are going to be corrupted. You don't know which ones because you don't observe which messages are being corrupted. But nonetheless, you're still able to just, you know, let the ablated K message sample go through the base policy you've learned and come up with a base action. So out of this n-1 messages, you know, if you wanted to construct ablated K message samples, then you can construct n-1 choose K such different samples in total. Some of them are going to be purely benign. Some of them are going to be contaminated. You don't know which ones. Therefore, you are going to come up with n-1 choose K base actions also, you know, based on these base policies. Then during the, you know, defense, you're going to make decision based on the ensemble of these base actions. So what it really does is that the agent would take a majority vote of all the resulting n-1 choose K number of actions. And essentially, this is called a consensus on action. Well, this is basically, you know, all of the algorithm that we design is very simple, but this simple algorithm has a very nice theoretical property of a certified defense by choosing K smartly. So we come up with a theory, basically is a certifiable defense theory, saying that this algorithm, you know, would have a very nice theoretical guarantee that, you know, the policy would be benign rather than being affected by the adversarial agents, based on the assumption that if the majority of the messages are benign, So basically means that you don't have more than n minus, half of the agents being adversary. And you also, assume that the purely benign k-message samples is going to be greater than the contaminated k-message samples. This seems to be a theory, assumption, but actually can be achieved by smartly choosing the k, as the details is showing in the paper. So the idea is if you choose k smartly, then you can guarantee that the purely benign k-message samples is going to be greater than the contaminated k-message samples. And also if you assume that the benign samples can reach some consensus, basically means that, the environment is not too noisy and, the agents are not all disagreeing with each other. And this is relatively a very mild assumption. Under all these scenarios, then we can guarantee that you will have an action certificate, which means that the selected action is guaranteed to be safe, to match the benign consensus. And you also have a reward certificate, which is saying that the cumulative reward is a lower bounded and it matches the natural performance under the benign situation. So the key message here is that this ensemble policy under any attack would perform similarly, similar to the base policy under no attack. So, we also did this evaluation on the food collector environment, where you have all these kind of agents are under different color with this black legs, which are the limited sensor range. So agents of their color can only eat food of their own color. But then there are also poisons that are red small dots that they should avoid because they would have a negative reward by eating the poison. So as you can imagine, because the agent can only eat their own food and they have limited sensory range, communication would indeed help them if the communication is benign. As you can see here in this figure, we can see that, all these kind of, algorithms can essentially gain information from benign communication. And our proposed algorithm, which is AME, indeed gains a lot of information from this benign communication. But we can see also our AME proposed algorithm is very robust against adversarial communications. So you can see on the x-axis, under no communication, right? It is much better when you have, under no attacker, it is much better when you have communication. But when you have C equals to 1, which means 1 adversarial agent or 2 adversarial agent or 3 adversarial agent, you can see our algorithm is much more robust compared with the baseline algorithms. Actually, what's very interesting is that although our algorithm theoretically in this case only certify 2 attackers, even when you increase the number of attackers to 3, it could still achieve a very robust performance, although theoretically it is not certified. So now, we're not stopping here yet. We wanted to consider a more realistic attack model because we know that some of the direct manipulation of the victim observation, or action, or dynamics may not be feasible. And indeed, we wanted to consider a more realistic attacker, but in the multi-agent system, which basically means that we'll have an adversarial player that can actually perturb the victim player. Is there a question?
Sorry, Dr. Huang, it's time out, so I think you'd be faster.
Oh, okay, I'll wrap off now. Yes. Well, so, this is indeed the end of, almost the end of my presentation. But here, I just wanted to say that with this more realistic attack model, we're able to achieve a very, impressive result, very different from the, supervised learning adversarial attack. We can achieve a certified defense by just doing adversarial training. So, this is very nice because we're able to bound some Lipschitz constant or Lipschitz condition of the multi-agent scenario so that we're able to achieve a certified defense by just using adversarial training in this multi-agent situation. And you can see experimentally, we can achieve very stealthy attacks and then achieve very nice performance. Here we use some kind of multi-scale, time-scale separation to achieve this provable defense using adversarial training. So lastly, I just want to summarize that, we've done a lot of work in adversarial perturbations in reinforcement learning, and to understand, these vulnerability of reinforcement learning powered by deep neural networks, when dealing with computer vision perception tasks using this interactive decision-making modeling. And, we've done, interacting with the environment, perturbations interacting with the environment, perturbations to interaction with other agents. We're really interested in understanding more about how to make these attacks more realistic. And that's the kind of work we're working on right now. I wanted to say thanks to all my students. Without them, none of these can be possible. And here is my email and my website. In case you have any questions, feel free to contact me. Thank you.
Sure. Okay, thank you.
So, Dr. Huang, due to time constraint, we may have to take the questions offline. So thank you. Let's thank the speaker again. Thank you.
Yeah, thank you.
Yeah.
We'll use your voice to okay. And I think it's pretty much ready.
I also share my screen here.
Exactly. I'm plugging the HDMI. I don't think you need it. Just we don't need it.
I think you need. Since online, need to.
Okay.
Not sure. Maybe not. Try.
Yeah.
Very good.
Yeah. It's okay.
That's if I move it up, move screen. Okay.
I think you.
That's a room share.
Oh, I see. No, sorry.
No.
Almost.
Sorry, it's okay.
It's still a correct on Zoom?
Yeah, it's okay.
Okay, so
let me do that. Yeah, okay. All right, please allow me to introduce our next speaker. So Professor Ludwig Schmidt joins the Allen School in University of Washington from his roles as postdoctoral researcher at UC Berkeley and a visiting research scientist in the robotics team at Toyota Research. His research interests revolve around the empirical and theoretical foundations of machine learning, often with a focus on reliable methods, data sets, and evaluation paradigm. Schmidt's research has led to more robust classification algorithms and new data sets and principles to probe the generalization capabilities of the neural network. Schmidt is the recipient of a Google PhD fellowship, a Microsoft Simons Fellowship, a best paper award from the International Conference on Machine Learning, and a Sprouse Dissertation Award from MIT. With that, Professor, you have the floor.
Cool, thank you for the introduction. Can people hear me like this? Raise the microphone, should be fine. Okay, good. Cool. So today I want to tell you about sort of like a little bit of my journey through robustness over the past 2 years, which led me to focus a lot on data sets. Okay, so high level motivation, I think we are all on board here, that the past 10 years have been super exciting in AI, lots of progress in computer vision and natural language processing and so on. But often when you take these research advances out of the lab and you put them in the real world, it turns out that machine learning methods still fail in a variety of ways. One very commonly cited example of that is self-driving cars. We had that example earlier today in Judy's talk. Other applications where it's very important to be reliable are healthcare, robotics, and now since it's 2023, obviously chat assistants. They are amazing, but often they also still fail in unexpected ways. Good. So we need reliable machine learning. How do we get there? And at a high level, I think it's good to think of machine learning as two parts here. One is algorithms and the other one is data. And typically when we do machine learning research, we focus a lot on the algorithm side, right? There are literally thousands, or I guess by now tens of thousands of papers on different optimization procedures. model architectures, loss functions, and so on. And that's fantastic. Sort of as a field, we have learned a lot about how to do the algorithms part of machine learning in a variety of different fields. But what we have learned less about is often how to build good training data sets. And there are much less papers which do similar rigorous ablation studies for training data sets. Okay, cool. And the plan for today is, first of all, to convince you that if we want to make progress in reliable generalization, the training data sets are actually really, really important. And in the second part of the talk, we'll look at what is sort of like state of the art in terms of multimodal data sets and how can we improve them. Okay, and if you have questions throughout the talk, please just ask me anytime. I'm happy to make this as interactive as possible. Okay, so let's get started with the first part. Why multimodal data sets matter. And in order to look at that, in order to do sort of like rigorous experiments and compare many, many different algorithms in a shared experimental testbed, we look at ImageNet. Obviously, it's a very widely studied data set. By now has about 15 years of history, and everyone knows this, right? 1.2 million training images divided into 1,000 different classes. We have the image of the dog here, and it should be classified as golden retriever. And while there has been so much progress on ImageNet, this is still a useful testbed for exploring robustness, distribution shift, and so on, because even in the widely studied ImageNet setting, state-of-the-art methods still fail in a variety of ways. And one way that people have started to measure this in a very precise way is by building new test sets for ImageNet. So here are a couple examples that are widely used: ImageNet v2, ObjectNet, ImageNet Sketch, ImageNet R. So the idea in all of them is, let's build a test set that we can just use ImageNet classifiers for out of the box. So these data sets share the same class structure as ImageNet, but something changed in the data set creation process. What exactly changed isn't really important for today. Happy to chat about it later. Okay, cool. And in order to get an overview for what's happening on these different data sets, we're going to look at this type of scatter plot in this talk. So this is out of a paper. We did a large-scale robustness evaluation in the ImageNet context. And sort of like the way to read this is that on the x-axis, we just put standard ImageNet accuracy. And then on the y-axis, we put accuracy under a distribution. Here, the starting point, ImageNet. And then we ran 80 different models from the seminal AlexNet over VGG, ResNet, DenseNet, and so on, to the state of the art in 2020, which was an efficient. Okay, so every blue point here is one model. And one thing that you already see is all of the models suffer about a 12 percentage point drop from this distribution. The dashed line here is y equals x, and all of the points are below the dashed line. And in fact, all of the points closely follow a linear trend. Why is a good question, but it's a separate story. So for now, we just use this as a given, because this is going to be really useful as a baseline. So in particular, if you give me a new ImageNet model, I can just look at its image. Let's say if you give me an ImageNet model, you can type the 1% of ImageNet. Then I can look at the spaceline and the trend, and I would say, okay, for 71% ImageNet model, I would expect to get 58% of ImageNet. And if your model indeed gets 58% of ImageNet v2, then I'm like, okay, this is a nice model, but not really outstanding. This is exactly what I would expect based on a trend from prior work. Okay, so what we instead would like to have is a model with what we call effective robustness. So effective robustness is going to be the low above this flat baseline. And we know this is the right target because if we want to achieve human-like robust generalization on ImageNet, then we should be exactly on the dashed line like this. So we did this experiment with 5 extra human lasers. Humans are indeed on the y equals x line. We would like to move the ImageNet models up, and this is what effective robustness measures. So for us, one important question with this large-scale robustness evaluation was, do any current robustness interventions like adversarial training, randomized smoothing, different forms of data augmentation, do they already help and give you effective robustness? Okay, in order to do that, we just ran 100 more models. Basically anything we could find on GitHub, we plugged into our testbed. Okay, and this is what we found. And your first reaction would be here like, Ludwig, this plot looks just like the one before. And this is indeed the right reaction. So basically the brown points here, these are the robustness interventions. They basically don't tell them. All of the brown models, all of the brown points here, the models for robustness interventions, they follow exactly the same baseline, the red line, as the models that are just standard trained on ImageNet. The only models that stand out by a little bit are the green points here. And these are models trained on a lot more data. So on the top right, we have a model from Google, trained on 300 million images, then a couple models from Facebook, trained on 1 billion images from Instagram. So this is now 1,000 times more data than the training set. And this is from the larger ImageNet collection of about 10 or 20 million. Okay. So this helps. It helps by a little bit, but it helps. Okay, all of this now was only in the context of one data set. We should obviously see if this also happens in more places, and it does. Just to give you one more example, this is the ObjectNet data set I mentioned earlier from Josh Tenenbaum's group at MIT, and overall very similar picture. So same idea. It's kind of plot here, x-axis ImageNet, now y-axis ObjectNet. The drop is now much larger, right? So ImageNet, we have 10% point, 5% drop. Here is now 40% drop. But overall, we still have a very nice linear trend, the red line here, where most of the blue models fall on. And then the only models that stand out with robustness above this red baseline are the green models trained on more data. Okay, cool. So this was state of the art as of late 2020. So we spent a lot of time setting up these benchmarks. We could precisely measure how good different models are. We saw some signal from more data, but it wasn't clear sort of like how far you can push the more data paradigm. And then something really exciting happened, because it turned out that OpenAI was working on the same problem for 2 years, and they pushed this more data paradigm a lot harder. So this is a CLIP paper. I'm sure everyone knows this here. This is from early 2021. CLIP and DALI came out around the same time. And so like the first set of results in the CLIP blog post where they announced the model was exactly that CLIP is much more robust than prior methods. So they compared this here, CLIP VITL, their largest CLIP model, with ImageNet trained ResNet 101. Two models with the same ImageNet accuracy, 76.2%. So this means in our scatter plot, we are on the same x-axis value. So now we get out of the distribution robust accuracy numbers here. What we're doing is we're exactly computing effective robustness. And then you can see that the effective robustness of this CLIP model is very, very high. Plus 6% on ImageNet V2. This is half of the drop. Plus 50 on ImageNet R, plus 40 on ObjectNet, plus 35 on ImageNet Sketch, plus 74 on ImageNet X, right? So you know ImageNet. If you get a small single-digit improvement on ImageNet, you write a paper about it. That's a good result. And here the CLIP paper came out with a large double-digit improvement on ImageNet now data set. So this is very, very rare, and I found this very impressive and wanted to understand what's going on. Okay, cool. So in order to understand in a bit more detail what's going on, let's look at this in the scatter plot visualization again. So this is again out of the CLIP paper, x-axis ImageNet. They used our abbreviation test bed, so this is visualized the same way. X-axis ImageNet, y-axis average over several natural distributions. Instead of just looking at ImageNet, V2 and ObjectNet and so individually, they just pragmatically average all of these together. And then the blue line here is again the baseline of the ImageNet trained models. The green points are the prior model data models. And then we have the orange line, which is CLIP and zero shot. So the high robustness numbers we just looked at, they are coming out of CLIP if you run CLIP and zero shot evaluation. And then you can see it has much better effective robustness than anything. The purple line we can do more. So there are two really interesting questions coming out of this. One is obviously what makes CLIP so robust? Why is the orange line so much higher than the rest? And the other one is what's going on with fine-tuning? Because there's one more line in the scatter plot, which is the red line here. So this is what happens when you take a CLIP model and you fine-tune it, the last layer fine-tuning linear flow to ImageNet. Then you make progress on the x-axis, but you actually lose some robustness on the y-axis. And if you do end-to-end fine-tuning, you lose even more robustness. So the second question coming out of this, can we get the best of both worlds? Can we fine-tune these models in a way that we don't lose robustness? Okay, because if you look at this, the best red points here, they're actually quite close to the prior more data models. And all of these prior more data models were also fine-tuned. So one thing we learned here was that fine-tuning can actually really damage your robustness. Okay, cool. So these are the two questions now. What makes CLIP robust is going to be the focus of the talk. If you're interested in a fine-tuning story, you can come to my other talk tomorrow in the prompting and listen workshop, because then I can tell you the story about how to tune these models in a robustness preserving way. We don't have time for that right now, unfortunately. For now, we are going to focus on the core cause for the CLIP robustness, which is all in the training data. So we did a very careful set of ablation studies last year to figure out where the robustness comes from. And the title of this paper already gives it away. Data determines distributional robustness in contrast with language image pre-training. Okay, so what did we do in the paper? Basically, we set up a long list of experiments to isolate all of these different potential causes of robustness one at a time. So one obvious one was language supervision, right? The CLIP paper was introduced as a method for combining language and vision. So that's new. That's something that's present in CLIP, but it's not present in the standard ImageNet supervised learning setting. The next thing is the training distribution. We don't know what the training set is. The CLIP training set is private at OpenAI, but it's not ImageNet. We know that. So there could be another cause for robustness. Another factor is training set size. So the CLIP training set is 400 million images, while most of the ImageNet models we looked at were only trained on 1.2 million. And then there are a couple more. CLIP is a contrastively trained model. Most of the standard ImageNet models are sort of like standard softmax classification loss. And you can do test time prompting with CLIP, but not with the standard ImageNet models. And the model architectures maybe also a cause, because the best CLIP models were vision transformers, and most of the standard ImageNet models in this benchmarks we looked at earlier were confidence. And the nice thing is, you can really pinpoint the robustness precisely to the training distribution. Again, how to do this, I'll have to refer you to the paper for now. But yeah, it's really just the training distribution. If you keep the training distribution to ImageNet-like, and you can introduce any of the other changes, you get no robustness. Okay, cool. So this was really interesting to me because we had all of these really challenging distribution shifts, little progress from existing methods. CLIP comes out, and it turns out all of the robustness in CLIP comes from a training distribution. Okay, and what you also just said, the CLIP training set is private. So the next point in this journey was, let's start building high quality public multimodal training sets, right? Because if the CLIP model is so good, we'd like to reproduce it and do science with it, use it in a variety of places. We need similar data sets. And this is now the LION journey. So you probably heard about this data set, LION 5B, an open large-scale data set for training next generation image text models. And basically what we did in LION was sort of like a first attempt at building a large image text data set at the billion image scale, so we can start training large CLIP models. Okay, so I mean, the name already gives it away. LION is about 5 billion image text pairs, half of it English, half of it other languages or not language specific. And this is 50 times larger than prior data sets. So before LION came out, the next largest public image text data set was 100 billion images. The cool thing about LION was that it got us into the same ballpark as the large data set from places like OpenAI or Google. And so like just for context, LION stands for Large Scale Artificial Intelligence Open Network. So this is very much a project driven by the open source AI community. There's a lot of really excellent people involved, lots of energy. This has been a very fun process, very highly collaborative with lots of institutions involved. Cool. So how do you actually build such a data set? So for us, the starting point was Common Crawl, right? So probably people have heard of Common Crawl. It's a non-profit organization that produces a monthly crawl of the web. Each crawl is, I think, a couple hundred terabytes. It is, by a side note here, it is amusing how central Common Crawl has become in all of AI, right? All of the large language models are trained on Common Crawl, and like all of the vision text models are also trained on Common Crawl. Okay, anyway, starting point Common Crawl. And then you do some basic web page filtering in order to extract only the images that have an alt text, right? If you know HTML, an image tag can have an alt text. So we use only those images with an alt text, download all of them, and then it's basically a lot of junk because it's the internet, the alt texts are not good. So you need to do some amount of content filtering. And as a starting point, what we did is the following. We used OpenAI's skip model, the EITB32, and we did the following content filter. For each image text pair, we passed the image through the image encoder. We passed the corresponding caption, the alt text, through the text encoder. And then we computed the cosine similarity between the image and text pair. And if the cosine similarity is above a certain threshold, we decided that's good enough, reasonable alignment between image and text, let's include it. Okay? And then we store the data, and then we are left with about 10% of the original candidate pool. And now if you ask, for instance, why threshold 0.3, I don't have a good answer for that because we are just like looking in a notebook. Oh, looked reasonable. Let's go with that. Okay, cool. So the obvious question with this entire pipeline here was like, do we actually get a good training set out? And the answer was yes and no. I mean, I think the first answer was very much yes. So if you look at what's trained on the live data set compared to the open checkpoints, then for smaller models like a we get basically the same accuracy. A little bit lower, but basically the same accuracy. And we also know that the differences are not due to changes in the training code, because on smaller data sets like YFCC, where we have matching training sets, we know that our training code matches the OpenAI training code. So these differences are coming from the training code. But then the problem is, as you scale up the models you train, you run into this problem that we have an increasing gap to the OpenAI. So on ImageNet, if you train a good VATL, it's a 3 percentage point gap. And then on ObjectNet, it's a 9 percentage point gap. And this was a bit of a bummer for me, because I mean, for me personally, the entire excitement, or a big part of the excitement with Philip, it's out of distributional. And this is still much better than out of the box ImageNet models, but this is also much worse than what OpenAI. So, okay, like overall, as I said, like this still has been very impactful. Like all the stable diffusion models are trained on Lion 5B. I think this was a fantastic starting point. Like won a best paper award, but for, like one big question coming out of this was, how can we make this data set better? Because it's clearly not as good yet as the OpenAI training set. Okay, and this is now the next chapter on this journey here, DataComp. Okay, so DataComp stands for Dataset Competition, and this has been a big collaboration of lots of people, mostly University of Washington, my home institution, Apple, Tel Aviv, Columbia University, Jülich, UT Austin, AI2, Lion, of course, again, Hebrew University, IFML, UIUC, TU Graz, Stability, and Google. Really fantastic team. I can't highlight all of the people here. I mean, the first 3 students, Samir, Gabriel, and Alex, they've been fantastic, co-leading this project. And then Yair and Vaishal have also been absolutely, I mean, everyone has been indispensable, but Vaishal and Yair also put on a lot of time. Cool. Okay, so what did we do there? Basically, the idea with DataComp was, let's just redo Lion all over again, but now in a nicely reproducible way. Like often when we have machine learning data sets, what happens is that people release the data set, but none of the tooling they use to build the data set. So basically then people have the data set, they can use it, but no one can build a new data set or like tweak how this data set was created. That's very different from when you think about like how we do model improvements, right? When we build on each other's modeling code, we very much release our modeling code, not just the trained model. On the dataset side, it's much more common to only release the final dataset, not the code you use to build the dataset. Okay, so our goal was, let's not just build Lion again, but let's also build out the tooling in a reusable way and release all the tooling, because that allows us to set up the sort of like data universe here as a machine learning benchmark, right? So if in a normal machine learning benchmark, the data set is fixed and we improve the model, we are going to turn this around in DataComp. We are going to fix the training code and we ask participants to improve the data set. Okay. And the goal is that then we can have sort of like a similar collaborative research approach on the dataset side, similar to what we have in model-centric research. Okay, so this is the high-level idea. A little bit more concretely, how does this look? So what do we provide? The core thing we provide is a large candidate pool of image text pairs from Common Crawl. So our largest pool contains 12.8 billion image text pairs that come out of Common Crawl. And then we take care of some of the very standard things like toxic content removal, face blurring to protect people's identity, some protection against data poisoning, and so on. But beyond that, we do basically no processing, because the idea is that you as a participant are supposed to help us figure out how we build the next version of Lion, like what are the right filtering methods. Okay, and then we have our standardized CLIP training code, and we have an evaluation test bed of 38 downstream tasks. So the idea is we're going to evaluate how good your model is by training a CLIP model on it, and then we can see how well the CLIP model does on 38 downstream tasks. And the competition has 2 different tracks. One is that we call the filtering track, where you're starting from Common Crawl, from our pool, and you're supposed to find a subset of good image text pairs. The other one is the bring your own data track, or short BYOD. If you think Common Crawl alone isn't good enough, I also want to train up my favorite combination of like Wikipedia, Reddit, and Twitter, then you can also do that. In the BYOD track, you can bring your own data. Okay, so this is the framework. And we don't just provide a single candidate pool, I should mention this, because we understand 12.8 billion is a lot of data. So we have 3 smaller scales. Each time we reduce the pool size by a factor of 10, so that researchers with fewer resources can also work on this. Okay, so this is all of this framework. Is this actually useful? And the answer is yes. As part of our competition, we also implemented a set of baselines. And this is our first data set coming out of data. This is one of the text pairs. And the cool thing now is that our new data set enables you to train a L14 model to better accuracy than the OpenAI checkpoint. So this is the same compute, same model size as the OpenAI model, but we are about 4% better on ImageNet, 5% better on checking compared to OpenAI. This is about 15 percentage point better compared to Lion. So this was personally for me very nice, because now we could close this robustness gap that we had on ObjectNet before. So to the best of our knowledge, this is the first public image text data set that's better than OpenAI's. And this is already in use at places like Anthropic, Apple, CMU, Meta. We gave these institutions better access. If you're using an iPhone, this is coming to you, to your iPhone. Cool. And you can also look at this in a different way. And that is, how much compute did we need before in order to hit 79%? We could push to 79 with Lion by training for longer and making the model larger, but that required 9 times more compute than training an L14 model with the blockchain. You can think of the status improvement as a 9x improvement in compute. Cool. And then, since we're in the end poor academics, our friends at Anthropic offered to send us a gift basket because they found data useful. This is very nice. Cool. And now we are getting almost out of time, but I can maybe briefly tell you about what goes into this new data set. So how do we make it better? And there's like 2 approaches that go into this. The first one is the clip filtering that we already had in Lion. And as I mentioned earlier, when we did this the first time, we didn't really know how to set all of these parameters. So this time we are a lot more rigorous with tuning all of these filtering approaches more carefully. So it turns out that being more permissive with the similarity threshold, the idea being that if you have more images, more data points, even if they're more noisy, this can still be better than just less. More data is just better, but you still want to do filtering. No filtering performs good. And the other thing is we took out the language filtering. Back in Lion, we still had English language filtering, but it turns out the clip model knows well enough if a data point is useful or not. And then the other thing is we do some image clustering, sort of like this first part, improved clip filtering. This is looking at image text alignment. The intuition was we should also look at just the quality of the images itself. And in order to that, we basically did some clustering of the data pool and of ImageNet, and then we removed clusters from the data comp pool that were far from ImageNet. The details in the paper, but then if you take the intersection of these 2 approaches, basically we have one data set, improved clip filtering, one data set, the image clustering, and then in the intersection of these 2 data sets is the one we just saw that outperforms the OpenAI one. Cool. Another important finding in this was that you can, like how do you come up with all of these different heuristics? One really important thing right now in AI, obviously, is scaling laws. Training big models is very expensive. So we would like to do all of our experiments at smaller scale. This was one of the reasons why we set up data comp in this multi-scale fashion. And then the cool thing is that the ordering of methods is nicely preserved across scales. So here, for instance, we have x-axis ImageNet accuracy on the medium scale of our competition versus ImageNet accuracy of the same approach applied to large scale version of our competition. And then the scatter plot here shows it's not perfect correlation, but it's pretty good. So we basically, most of our exploration at the medium scale, then some experiments at large scale, and only very few experiments at the extra large scale. Cool. Okay, so far so good. I mean, so this talk was about the data being really key for out of distribution generalization. But I think it's fair to say that for all sorts of breakthroughs in the past 2 years of AI, large internet collected data sets have been the key ingredient. Like another thing that was super active last year, and obviously still very active, is text-guided image generation, like DALL-E, Imagine, Stable Diffusion, and so on. And the core ingredient here is, again, large image text data sets. You can use autoregressive modeling, you can use diffusion models. What they all need is a large image text data set. And then, of course, in language modeling, similar story. There are different architectures like GPT, BERT, T5, but what they all rely on is having a large internet harvested training set. So I think this is going to be a really important direction for machine learning going forward, because we know relatively little about how to build these large pre-training data sets. They are key now to all sorts of models that we train, but our curation approaches for internet scale data sets are still in sort of like early days. And so like people throw together some data, train a model, works really well, but I'm sure there's a lot more to learn here and a lot more to improve our pre-training data sets. Cool. So then I'll just leave you with our URL, datacomp.ai, and I'm happy to take questions. Thank you.
So what do you think, for example, with the current model? So how do you think about that?
Yeah, that's a great question. I think obviously one direction here is using synthetic data to complement or even replace real data would have advantages. I have not seen. Okay, then the question is often sort of like, what is the baseline, right? So I think there are nice initial investigations in this direction. I think one thing to keep in mind is if you use images that come out of Stable Diffusion, and Stable Diffusion is trained on Lion 5B, your baseline is always just training on Lion 5B directly. And I haven't seen methods yet that outcompete directly training on a large training set. I have seen methods that, for instance, compare, okay, let's generate 1 million images from Stable Diffusion, and let's compare it to 1 million images from ImageNet. And then you can maybe do better with the 1 million images even from Stable Diffusion. But that's not really a fair comparison, because you're comparing 1 million real data points to 5 billion real data points in Stable Diffusion. So I think the challenge is sort of like, can you actually outperform directly training on your source set that you use for training the generative model? Cool. Good question. Thank you.
Can I ask a follow-up question? Yes. So, just following with the Dr. Charles asking. So I guess maybe 3 years from today, the internet will be flooded with generated data. It's hard to tell real ones from fake ones, the generated ones. So any comments on, for example, the next generation of facing this issue? What do you think?
Yeah, that's a great question. I mean, I think one good thing is that there's still a lot of images on the web that are not parted offline. So as I mentioned earlier, it's about 50 billion, or I think actually 80 billion image text pairs. And if you look at the images without an alt text, there's like a couple of 100 billion more we can use. So it's not like we are running out of data. Eventually we may, but we're not running out of data yet. So a simple thing would be just to say, oh, let's only use snapshots from before 2023. We could do that for a while. Then when it comes to detecting generated images, I would have to look at the literature, but my feeling is if you generate an image and you don't specifically have a generator that tries to evade detection, like a simple classifier can probably figure out if it's coming out of a Stable Diffusion model or if it's a real image. My guess would be that some image statistics are pretty different, but I'm not sure. I mean, probably someone has run this. If someone knows the answer, let me know. But my guess is we can distinguish between them. Thank you.
开一下，OK。
All right, so we're at the almost the end of today's workshop. Please allow me to introduce our final speaker of the day. So Dr. Chao-Wei Xiao is an assistant professor in the computer science department at Arizona State University. His research interests lie at the intersection of security, privacy, and machine learning, with the goal to build this socially responsible machine learning systems. He obtained a PhD degree in computer science and engineering department from University of Michigan Ann Arbor, and his bachelor's degree in School of Software from Tsinghua University in 2020 and 2015, respectively. Now, Professor Xiao, please take it away.
Yeah, so thanks for the introduction and thanks for inviting me to this workshop. Yeah, so thanks for the introduction and thanks for inviting me to this workshop. So today I want to discuss something about like the transformer AI and what the new opportunities by the introduction of the foundation models and the generative AI. So yeah, actually what is new like recently, so the concept of foundation model proposed and also with very large like data set, like a lot of like we can train very powerful models which can work on diverse data set. And also on the other hand, the diffusion model like has been proposed and it can generate a very high fidelity like data and high quality data. So here I want to discuss, so what are the new opportunities in terms of this like a trustworthy or in terms of the safety by giving this like a new like foundation models and generative AI. So we talk about a lot of things about the machine learning, talk a lot about the success stories. So in this workshop, I think we mainly want to talk about the problems. So we know machine learning has the problems, like for example, in 2016, there is a car accident caused by the autonomous driving cars and killed one person in Florida. So after the investigation, the cause of this accident is the autonomous driving systems. It's not designed to always detect the vehicle cutting in front with a light detector. So why it happens, to answer it, we know like in the traditional machine learning, there is a strong assumption that the distribution of the training data are similar to the distribution of the test data. However, in the real world, we will meet more complicated scenarios, which means that we will meet some like unsafe data or which the data are not shared the similar distribution of the training data. Then it introduces the problems. So I think the previous speakers talk a lot about the robustness setting. So here I hope to talk about the other setting which we consider the worst case scenarios by assuming the attackers in the systems to evaluate what is the worst performance of the systems and what should we do. Usually, like when we talk about the like problems, we should put it into the machine learning pipelines. So usually we have the training stage and test stage. So similarly, it will have the training time attack and the test time attack. So in today's talk, I will mainly talk about the test time attack, which will assume the model has been freezed. So what is the threat for this model? What is the adversarial robustness for this model? What is the worst case scenario for this model? So actually, we are living in the adversary environment. So which means that there is a lot of like hackers behind the systems. For example, when the ChatGPT has released, so in the Twitter, I think almost like 19% like users are aimed to study what is the bad performance or what is the weakness of those kind of like models by generating diverse prompt, do this prompt injection, all kind of like things. So from this example, we can say that actually, so we are living in the adversarial environment. So we need to know what is the worst case of these systems. So I think you already seen many times about these examples, like attackers show that they can systematically like optimize the perturbations and add the perturbation to the image to mislead the model. And for our humans, it cannot mislead our humans because it is bounded by the LP distance. So when this problem was proposed like 10 years ago, so they use the LP based distance, and before like investing the after that, there is a huge amount of more advanced attack or defense method proposed. So here I want to say that before moving towards to more advanced attack or defense method, we need to go back to think about fundamental questions. It's like, is the LP enough? So is the LP the only three models? Otherwise, it will constrain us to start a very limited problems in this domain. So definitely LP is not very good. So the reason why we bound LP because we don't want the data mislead the humans, right? So we use LP as a like perception matrix to evaluate the lookalike. But if we change the, for example, lightening of the images, it will introduce the large magnitude in terms of the L2 distance. And also if we shift in the pixel positions, it will introduce the large magnitude in terms of L infinity distance. But for our humans, we all recognize it as cat, and there is not a huge perceptual difference. So it motivates us first to think about whether beyond LP it exists as adversarial examples. So the answer is yes. So LP, you can view it as we add perturbation to the images. So beyond this, a simpler way to do it is like maybe we can shift in the pixel positions. And in this way, like we can use the flow to represent the pixel displacement. And in this way, we can generate a new type of adversarial example, which we call it as a special transformed adversarial examples. And this is a virtualization result. We can easily say that from the last row, like the first two rows are the perturbations bound. Under the LP-based thread model, we can say that as a background area, there exists some perturbations. But for the special transformed adversarial examples, we can say it moving the pixel positions. So it shows that beyond LP, it indeed exists. And even like we can make the perturbation has the semantic meanings. For example, we can make the person smile and it can mislead the model, or even we can make the person wear a glass, it will also mislead the model. And also those kind of adversarial examples can also like attack the black box models. It can attack the industry level system. For example, here it attacks the Microsoft Azure, although we don't know any parameter of those models. And also there is active research like to input generate the high transferable adversarial example, such as Shanghai has some very great work in that directions. But today, I mainly want to talk about the defense, talk about the solution, given the concept that we know like there is not a single limited like thread model for the example. Adversarial example indeed exists beyond the LP space. So what is the solutions for these problems? So I hope to borrow a slide from Zico. So I really like these slides. So actually, there is some like agent predictor. So what is the performance among these 4 tasks? So they predict, for example, at 2025. So what is the performance looks like? So they select 4 tasks, and the result shows that 3 of those tasks are like the actual performance today is by the machine learning model are like beyond the expectations. So for example, for the mathematical problems, it has a huge improvement due to the introduction of the large language models. And also, so for the adversarial robustness task, this is the only one which is beyond the predictor performance. So it shows that I hope it gives you a little bit of sense like that this problem is not easy. So the reason why this problem is not easy because usually if we want to train a model, we can get decision boundaries. But for this decision boundary, we only can collect the limited data. And the space which contains the adversary is very huge. So for any space, like we do not cover so the decision boundary is not covered in the high dimensional space. There is a lot of like a black hole. So if the data is located in those areas, we don't know the answers. So that's the problems. And in this community, like also proposed by many great researchers, the adversarial training based method proposed. So the high level idea is like instead of to just minimize for example, the entropy loss, what they are doing is like we can optimize a min-max, we can do a min-max optimizations. So for the min-max optimizations, it first solving the inner maximal process. So for example, we can approximate the inner maximize process by finding the worst case adverse examples. So in this way, for example, if we have a model, so then we generate some perturbation and we added it to the input data, and we want it to maximize the loss L. So for example, for this red point, so this is the data what we can generate. And then we update the model parameters. And in this way, like we can change the decision boundaries to make it can cover those data. So this method proposed, although it has been proposed for several years, but like it is still be the most effective ways, like most effective method. And also with the proposed like generative model, for example, the diffusion models, some researchers show that they can like use the generative models to generate the data, and then they do the like adversarial training on those data, it can improve the performance. So although, for example, they use this like generative models, but it still like can only works on the single type of perturbations. So here I want to ask questions like, is the adversarial training the solution? So in this domain, if you do the literature review, like almost like 19 papers are related to use the adversarial training as a solution in this domain. So in today's talk, I hope to talk about the problems of the adversarial training. This method is very, very great, but it also has some like intrinsic like limitations. So first is like, so for the adversarial training, so during the optimization process, in order to solve the inner maximal process, we need to have the Thread model. So it means that for this whole process, it is trained on the same adverse example. So for example, if we give it a new type of adverse examples, for example, the special transformed adverse example, which I showed before, so it does not work. So here the number is the error rate. We can say that it can still attack the adversarial trained robust models. And also some researchers show that although like we know the perturbations, however, there still exist in multi-type of adverse examples. So can we combine them together to train a robust model? And also the answer is not true. So they show that for the adverse example, it has the mutually exclusive properties. So if you combine them together, so you can get a model which the performance is lower than the model which is trained separately. And so to solve the, if we still want to go this like adversarial training lines, so the key is like we need to propose a Thread model which can cover the diverse like perceptual space. So based on these ideas, there are some researchers from Maryland. They propose this perceptually adversarial robustness. So instead of using the LP-based model or the special transformed like Thread models, what they propose is that they use the perceptual matrix as the Thread models. For example, they can use LP-IPS as a Thread model. So the good thing is like for those models, they directly generate those type of adversarial examples. And the good thing is that it can cover this LP or special transform the adversarial example, cover the space, so it can cover a diverse space. But the problem is that, so in order to solve the min-max schemes, it is not very straightforward to solve that. And the performance is also not that good, we can say. So this is the like one, like maybe problems for this adversarial training based method. Another problem is like, so for the current, in the literature, like the adversary training based method mainly started still on the classification task. But nowadays we will meet a more like a complicated task. For example, in the autonomous driving systems, we also have a very important like task, which is planning all the predictions. So for this like prediction models, different from the traditional deterministic models, it is like generative models. So to train a robust generative models, trust me, it's not very straightforward. So in our cover papers, we do a lot of like customizations to make it works. So this is a non-trivial. Or even for the classification models, if we change it from the 2D to 3D space, it also does not work. So we train a robust 3D models, although it can achieve very great performance in terms of gradient-based attack. But we found that those type of models exist in a huge like gradient masking problems. So if we perform a black box attack, the robustness will be very, very low. So it means that adversarial training cannot be directly applied to the 3D domain. And also like today's, as like a previous speaker said, like we already will play with like the community already play with the Lion, the larger and larger data set. But in the adversarial community, we are still play with the CVPR. So Sihang has a very great works to push the boundary to the ImageNet scale, but we are still not like really move forward in terms of the skill, data skills. So, and also to do the adversarial training, we need to retrain the models. It also needs to introduce extra computational cost. And although there is some like efficient adversarial training based method proposed, but it still like have some like computational cost. And it's still like preventing it to the more large scale like data set. So, and also for these communities, like this is like calculated by the Nicholas. So it shows that in these communities, there are more and more papers proposed. But most of these papers, if they started like adversarial robustness problem, they still focus on the adversarial training like directions. So I think adversarial training is really, really, really great. So I think it gives the directions at the beginning for these communities. So what is a way to build a robust models, and it consistently shows the most effective like way. But what I want to say that today is I think we should not like just like put like a 1% improvement or 2% improvement on the simple CVPR data set in terms of the L2 like perturbation or L infinity perturbation. We really need to think about like given the diversity of the perturbation types, or given the like new dynamic like landscapes of the threat. So how should we propose a fundamental way to define against the unseen adversary example or the dynamic changed adversary examples? So how can we move forward in these communities beyond after the era of the adversary training? So what should be the like solutions? So beyond the adversary training based method, there is another method that we can call it as purification. This is another direction. So for these directions, we don't want to change the parameter of the model. So we hope to directly use a pre-trained model. So for the downstream models, no matter like it trains on the Lion or it is what kind like foundation models, we directly use that. We don't want to change the parameter. So what we want just to do is like, we want to add a purification module in front of this pre-trained downstream task. And the goal is like, we want this purification module to remove the adversary effect. So we want it can remap the adversary example back to the nature data distribution. So you can clearly see that the difference between the adversary training and the purification, those two directions. So for adversary training, it's like we update the model parameters. And for the purification, it's like we don't update the model parameter. We just carefully design the purification model. And because here we don't change the models, we directly use the pre-trained models. So definitely there is no so-called seen perturbations. So then it can definitely like defend against the unseen perturbations and seen adverse example. And at the same time, because we don't change anything about the downstream models, so it can directly work on the diverse data set, because no matter what downstream data set you give the models, you can directly give it by just the injection like a purification module in front of your like downstream models. And also we don't need to train the downstream models, so then it will have the very low computational cost. And we can leverage all existing advance of the different model architectures. So it is very great. So how to design it is the key. So what should be the purification operators? So at the beginning, maybe the most straightforward thing is can we use a blurring? So at very early stage, some researchers show that they add an average filter, but the problem is that there will be existing the adaptive attackers which can still adaptive attack your system by assuming they know every knowledge about your defense method. So for example, if I know you will use the blurring as a defense method, so we can easily as attacker, we can easily design the stronger attack to attack your system again. So it will not end the attack and the defend game. So that is not the good way. So how about the edge? So for our humans, so we are robust to the change of the edge, right? So, but we are insensitive to the pixel changes. So how about the edge? The advantage of the edge is we can design the robust edge detection algorithm, because there is a lot of traditional edge detection algorithm, non-neural network based. So we can, for example, for the canyon, we can carefully design a robust canyon algorithms. In this way, it can remove the adverse perturbation. And then after giving the, for example, the RGB image, after the robust edge detection, then we get these edge images. We show that it can improve the robustness, but the problem is it also lost a huge amount of information. So then the performance is still not good. So what is the way? So can we leverage the recent advantage of the generative model? So here we think the answer is the diffusion model. So what is diffusion model? So just simply show it is it has the forward process and the reverse process. So for the forward process, what we are doing is we just add some perturbation to the images step by steps. So we add the Gaussian noise to this image and step by step. And from t equals to 0 to t equals to the 1. So at t equals to the 1, then all the we add the Gaussian noise to make it as a standard Gaussian noise. And then it has a reverse process, so we can remove the noise by step by step. And finally, at t equals to 0, then it will back it into the nature data distribution. So this is the adversary example. So this is the diffusion model. So why the diffusion model is a good way to serve as a purification model. So here, let's go a little bit mathematical things. So for the diffusion model, it has a very good properties for adversary robustness. So here, let's assume that we have a PT and a QT, which are the distribution at time step t through the forward process of the diffusion model, and the starting point is sampled from the clean data and the adversary data respectively. So we have proved that the chaos divergence of the PT and the QT are monotonically decreased when moving t from 0 to t equals to 1. So if t equals to the 1, then all the PT and QT becomes to the standard Gauss distribution. So the chaos divergence is 0. So it shows that there existing some a t, which that we can remove the adversary perturbations, but at the same time we can keep the semantic meaning of the data. So if t equals to 1, it definitely can remove the adversary perturbations because all the PT and QT are now the standard Gauss distribution. But it also removes the label semantic of the input. So in this way, if we feed it into the reverse process, then it also, although it can give you a high quality image, but maybe the input is like a cat, maybe the output will be a dog. So that's the problem. So T is a hyperparameter, so it cannot be too large and it can also not be too small. Okay, so we know like T is a hyperparameters, then we can propose our like purification pipeline. So we call it as a DiffPure. So the pipeline is very simple. So we just leverage the two like a pre-trained model. So we just leverage the pre-trained diffusion model and leverage the pre-trained like downstream models. So given the input, if it is adversarial input, so we feed it into the forward process by adding the Gauss noise step by step. And then we, after certain step T, we feed it into the reverse process, and then we get the clean data. Oh, not clean data, we get it, the purified image. And then we feed the purified image to the models, and the model will give us the correct prediction. And here is some like a qualitative result. We can say that after the forward process and the reverse process, finally we can get a very like clean images and for our humans. And we also show that most importantly, like it can defend against the diverse adversarial perturbations. And all of these adversarial perturbations are unseen for the data because here we directly use the pre-trained diffusion model and the pre-trained downstream task. They never see any like type of perturbations during their training. But due to the good property of the diffusion model, it can actually remove the adversarial perturbations, so that it can show a very high like robustness in terms of diverse attack. So here we evaluate by using the empirical like strongest like adaptive attack as far as we know. So, but as I mentioned, like here, the number what we got is by using the empirical attack. So then maybe you will ask me like whether the performance will be lower. So maybe, so in like later years, there is some researcher from Google, they show that they can reduce the robustness a little bit, but it's still not that low. So it's still very high. So it still shows that it is true, really like robust. So we open source the models. So we really welcome you to attack this. So this also introduces another problem. So because we want to show why there's a diffusion model is the solution. So we really need to give some like theoretical understanding. So previously what we provide is just the empirical robustness. So it means that maybe there existing some like data which can attack your model. For example, you can view it as this blue cycle. So this is a decision boundary. So maybe there existing some like data in this region, it can still attack your model. So it can lower your like report accuracy. So the true robustness is this black like region. So but because the neural network is the non-convex like model, so it's really hard to calculate the true robustness. And also another like robustness, we usually call it as certified robustness. So it is a lower bound like robustness. So it if we provide you a like certified robustness, it means that no matter how you attack the model, you cannot lower than this number. So here we want to say like whether the diffusion model can enhance the certified robustness, because in this way you can trust me like, okay, it indeed improve the robustness, right? So here in our work, so we show that the diffusion model can indeed enhance the adversarial robustness. So here we do some like theoretical analysis, and we show that you don't need to know the details, but it's just to show that by using the diffusion model, it has a high probability to map the adversarial data distribution back to the clean data distribution with the same label semantic. And also like why it can provide the more like higher like certified robustness is because so originally like if we do the randomized smoothing, you still will each data as a single point. So for example, this is the robust like region for this single like data manifold. So this is the blue cycle is a robust region. But with the diffusion model, it actually maps each single data back to the data distribution, the union of the diverse like data manifold with the like a label semantic. So in this way, it can like the new robust region by after the diffusion model is the union of the different like manifold with the same symbol label semantic. Then it has the probability to provide you a lot of like robust readings. And because the diffusion model map each single data to the data distributions, then we propose the certification-based method, which we do the sampling through the reverse process and to estimate the data distribution of the diffusion models. And in this way, we can show that it can indeed like improve the certified robustness a lot. Also, it achieves the state-of-the-art certified robustness in terms of L2-based perturbations. And also, as I mentioned, like for the adversarial training, so in the 3D domain, it does not work. So how about the diffusion model? Whether it is a solution, we also need to evaluate it through the diverse like task. So here we apply this idea into the 3D domain or the audio domains, and we show that it can indeed improve the robustness. So how long do we have? 3 minutes. Okay, so because we only have 3 minutes, so I just want to introduce another thing. Is like so today I think for the trustworthy is so it's not only like the trustworthy from the perceptual space, which means that we build a robust like perceptual models. It's more about like the also including like how we like the final goal for the trustworthy is like we want to reduce the gap between the human and the AI, right? So the trustworthy is proposed from the human perspective. So that is our final goal. But for our human, we are not only have the perceptual system, or we have the reasoning system. We actually have also can do the actions. We will interact with the world and we can solving multiple tasks. So here I want to propose that we also need to think about how to build the trustworthy agent, which can be like run in the open-ended environment and solving the dynamic like task automatically and reliably and without by introduction interacting with the real world. So recently, like our group at NVIDIA, so we propose like Voyager, so which is an open-ended embodied agent by using the large language models. So in this works, what we aim to show is like we want to build the reliable open-ended embodied agent by using the large language models. We hope it can solving the dynamic like task in the like open-ended environment in the open-ended world, such just like our humans. So yeah, maybe due to time limitation, so I will not introduce it. So I will stop my talk here. So any questions?
I have a question regarding the purification process. You said that diffusion models are very good for the purpose, but they have its downside that they have to solve different style.
Yeah.
And other is perhaps displayed by open others. I mean, you compress and code and decode the data point, and would those adversarial additions also be erased in such a process?
Yeah, it will. Yeah, so we try to use the ODE and it is still existing. We can still attack the models. So the stochastic SDE is very important to maintain the robustness from our experiment. And in terms of the inference time, I totally agree with you. So we cannot just use a single steps to achieve the high robustness, and how to reduce the inference time, I think is a very promising direction. And what we are also currently working on.
More questions?
Yeah.
So does purification, like performance of your diffusion model for the purification depend on the type of change that you apply to the image?
Yeah.
I don't know, the global level or the local level?
Yeah, so here we show that in our previous work, we just show that it works on the invisible like perturbations, such as L1, L2, or L infinity, or the spectral transform perturbations. And we show that for example, the adversarial patch for this like perturbation, which has the visible patterns. So the diffusion model is not as that good as to handle those situations. So we need to propose the new pipeline and strategy. And in our recent work, we show that by changing the pipeline a little bit, like we can also defend against the adversarial patches. So we will have an archive which will release very soon. Yeah.
Thank you. Further questions? Let's thank the speaker again.